It was okay.
Please grab a seat and welcome to the last day of the conference. All right. All right. So the first speaker of the session is Buhrman from the University of Amsterdam, and he's going to talk about quantum superposition verification. So it's all yours. Use this mic.
Thank you very much. It's a pleasure to be here. Also, thanks to the organizers for having this strange guy talk at this conference, because I feel a little bit out of my depth, coming from quantum information, which I was working in basically almost from the beginning in the mid-late 90s. And then quite recently I made a big decision to reduce my academic position to 1 day a week at the University of Amsterdam, and I moved to a company called Quantinium in London. So that has been a really extremely interesting journey. So I have to say a little bit about Quantinium. So since I'm now working for a company, I say a little bit about what we do. We build quantum computers, it's based on the platform that works with trapped ions. The ions then correspond to the qubits that can be 0 and 1 and in superposition. And here you see a picture of our currently available system online. If you're interested, contact me. And it really works with these ions that are shuttled around. Here you see a picture of the ions moving around in the trap. And these ions can also switch place, so they can jump over each other. Well, they don't really jump, but they switch place. So you have any-to-any connection, so any qubit can be connected to any other qubit. And then here you see these gray zones. These are gate zones, and these qubits, single or double, can go in there. And then with lasers, you can do 2 or 1 qubit gates on them. And this is all working quite well. I'm actually not an experimental physicist, so this is fantastic for me to see. And then the next step, and this is already working in our test labs, is to go from this racetrack design to a grid design, and then you can even put more ions on there and still have this all-to-all connectivity. And then here you see our roadmap that was unveiled a little while ago, half a year or so, where we're currently at the 2025 stage, where we are in the process of unveiling and making available this computer Helios, which has about 100 qubits. We already have access to it ourselves. And as you can see, the error bars, so the errors that you make when you have a 2-qubit operations, are quite low. They were 10 to the minus 3, and they're now going towards 10 to the minus 4. And that means that you can do 1 over that many gate operations. So you can start to do longer and longer computations. And then with error correction and even further down the road, fault tolerance, you can make this error smaller and smaller. And so you can do longer and longer computations. And as you can see, the prognosis is that in 2029, we will have thousands, up to 10,000 of qubits available. And so this is sort of very, very interesting, because we're now entering a stage where these computers can compute things that you cannot compute anymore on a classical computer, not even if you have a supercomputer using fancy techniques. So it's sort of very exciting for me. So this is a little bit of intro to my talk, but I'm really going to talk about something else, not the computer. As you can see here, there are a couple of applications that quantum computers have, and I'm going to zoom in on the crypto side of things, on the quantum communication side of things, because that, I think, really ties in with the theme of this workshop. As you will see, there are some really interesting tight connections. So this is quantum position verification. By the way, not quantum superposition verification. That will be an interesting other topic, but that's not what this is about. And this is joint work with a bunch of people that you see here. And so the story starts a bit with the following. In 1969, man landed on the moon. But actually there is a staggering almost 30% of the US population who thinks that never really happened. And this whole thing was staged and is one great hoax. And it was really took place somewhere in New Mexico where it was filmed, and there was nobody on the moon ever. And so this begs the question, how can you prove that you are at a specific location somewhere on Earth and somehow convince other people that you actually were there? And that's the topic of this talk. And I want to sort of lead you through some of the ideas that have emerged in this field. But first, sort of the ideas that you want to prove that you are at a certain position in space. And for example, that means that, for example, if the launch missile command comes, then you can check that it really came from within the Pentagon and not somebody else was trying to spoof you and claiming that happened. Or, for example, that you are talking to South Korea and not North Korea. And another one I have on my list is the pizza delivery problem, where you play a prank with your neighbor who you don't like, and you order 100 pizzas for his place. And then at some point, 100 pizzas arrive at his doorstep, and he's of course not happy with that because he didn't order any pizzas. Well, if the pizza delivery or the pizza restaurant, which is actually very, now I realize, very relevant here in Naples, had this position verification protocols in place, then this could never have happened. And when you have this position verification, you can use it as a building block for even other things, like authentication. And for example, you can then have primitives where you can only read a certain message if you are at that particular location. And if you're not there, you're not able to read it. So it sort of leads to, I think, an interesting set of primitives for cryptography. Okay, so let me set the stage and explain to you exactly what I mean so that you have an even better idea. So position verification is the following, and I'm actually now not going to 3D space, but to the line, to 1D, because that's much easier to think of, and moreover, all the problems and sort of possibilities and impossibilities already arise in this simpler setting. So that's why I'm focusing on this sort of 1D setting. But believe me that everything I'm saying sort of carries over to the 3D setting. It only becomes slightly more complicated to explain. So we have the setting, so we have a prover who claims to be somewhere in between these two verifiers, and these two verifiers are the ones that need to be convinced that there is somebody at this blue line. And I just threw the blue line in the middle, but it doesn't matter. It could have been anywhere in between these two verifiers. And so the assumptions are the following, and somehow this ties in a little bit already with the workshop. So the communication that occurs goes no faster than the speed of light. And I'm making a strange assumption saying that the computations that occur instantaneously. That's not true. So that will actually sort of limit a little bit what I'm saying, but bear with me. For now, I'm just assuming that the computations go at the speed of light. And moreover, these verifiers, which I called verifier 0 and verifier 1, they can coordinate. And they have coordinated and they have agreed upon some protocol, and they may have also some shared resources. And now, okay, so this is all nice. What do I want to accomplish? I want to accomplish the following: that there is no coalition of fake provers, namely, call them Alice and Bob in this case, that are sort of sitting somewhere on this line, but not at the blue spot. So there's nobody at the blue spot, but nevertheless, this pair, Alice and Bob, try to convince the verifiers that there is someone. And I want to prevent this from happening. Okay, so this is the honest situation where there really is somebody there, and he performs a protocol with the verifiers. And the verifiers should be shielded from this situation where there isn't anyone at the blue spot, but there are two cheaters trying to spoof this protocol. So let's see a protocol that sort of makes sense. And this is already old, from the early 90s, actually not meant for this, but it's the following idea. Suppose that time flows from top to bottom in this case. Assume that the verifier 0 sends a random bit string x to the prover who's sitting at this blue location, and the prover immediately on receiving this sends it back. And the verifier times how long it took before this message came back. Now, if this takes a certain amount of time, then the verifier is certain that the prover could not have been further out than the time it took from X to go to the prover and go back. Right? So it sort of gives an upper bound on how far away the prover is from verifier 0. And now let's do the same thing from the other side, send another string, Y, and the prover, upon receiving that, also immediately sends it back. And there's also a timer that times how long this took. Then these two sort of light cones intersect in precisely 1 point, and that's where the prover is supposed to be. This sounds like a nice protocol. So let's see if it can be attacked by Alice and Bob. And lo and behold, it can be attacked, because here we have them. And what Alice can do is, upon receiving X, she can sort of intercept it at an earlier point in time, store it for a little while, and then when the time comes, she sends it back to verifier 0. And so from verifier 0's point of view, it looked like the string came from a prover that was further out than Alice actually is. And Bob can, of course, do the same thing, intercept Y, store it for a while, and send it back. And so this protocol now is completely broken, and there's nobody at the blue spot. But from the verifier's point of view, this was a completely honest run. Okay, so let's make it a little bit more complicated, because maybe this X and Y, they should have sort of interacted somehow. And so let's do that. So let's assume there is some function that is computed that, depending on the inputs X and Y, outputs some values A and B. And the A and B really depend heavily on what X and Y are. And so then the prover, upon receiving both X and Y, immediately, instantaneously, and so this is unrealistic, but bear with me, computes this function f of x, y, and sends this A and B back to the verifiers, who then time whether everything was on time. So this looks like already a more interesting protocol. Let's see if this can be attacked. And unfortunately, this one can also be attacked, because Alice just does as before. She intercepts X early, but then makes a copy of it, because it's, after all, just classical information, stores one copy and sends maybe the original one on, just as if it was sent honestly. And Bob does the same thing. And now if you complete this diagram, you can see that at this point in time, both Alice and Bob have X and Y, and so they can quickly compute f of x, y, and send on the perspective A and B to the verifiers. And again, from the verifier's point of view, everything is hunky-dory, and it looks like there's somebody at the blue spot, but there isn't. And so actually, this is a proof, almost in all generality, that classically you cannot have a secure position verification scheme, because you can always sort of intercept information, copy it, and send it on, and somehow fool whatever protocol is there. So this it really proves that you cannot do this classically. So classically, there's actually not much interesting going on. So it will turn out to be good to forget a little bit about the timings and look at a game that somehow is versed from the point of view of Alice and Bob, that shows what is needed for them to break a protocol. And I call this the attacking game. And the attacking game from the previous protocol is the following. So we have this function f that is somehow known to everyone. And then Alice and Bob get an input x and y. I don't talk about timing anymore. And then they are allowed to send a message to each other, but independent of each other. So Alice sends a message to Bob, and then she receives a message from Bob that was sent to Alice. But the messages are independent of each other, so that's important. It's not that Alice sent a message to Bob and then Bob can do something and send something back. It has to be like this. You can think about it, that makes sense. And then they have to output A and B. So this is the game that Alice and Bob have to win. And as we saw before, if Alice just sends X and Bob sends Y, then they can play this game perfectly, this attacking game. But you see here that information needed to be copied, right? Because Alice needs to keep a copy of X at home in order to compute f of x, y once she receives y. And you see now there's some possibility here, because if you would play this somehow quantumly, then you cannot play this copy strategy. So there's some room now to do something interesting for in the quantum setting. And by the way, this attacking game, I call it the first inversion of this talk, because what has happened now is we set out to design an honest protocol that achieves something, and we have now gone into the mindset of Alice and Bob that attack it. And I'm now going to focus on these attacking games and analyze them. So this is the first inversion, a little bit in the spirit of Bach's music, who also had these nice inversions. Okay, so let's go for a quantum protocol, and here's one that looks actually very promising. It's the following. So verifier 0 sends a qubit now to the prover, and verifier 1 sends a bit to the prover. And the prover, upon receiving both these items, sends or routes this qubit onwards to verifier B. So if B is 1, then he sends the qubit to verifier 1, who then checks that it indeed was this qubit. And if the bit was 0, he routes it back to verifier 0. And all of this has to time in the right way. Okay, so let's study the attacking game for this protocol. And here's the attacking game. So Alice receives an unknown qubit psi, Bob receives a bit, and they are allowed to send a message to each other. And then at the end of the day, if, we can assume safely that actually the message that Bob sends is just this bit B, because he can just copy that information and send it on. It's classical, so without loss of generality, it's B. And if the bit is 1, then Bob has to be able to produce psi. And if the bit is 0, then Alice has to be able to output psi as well. And now if you stare at this a little bit, you can see that you made a cloning machine, right? Because Alice has to send a message to Bob, not knowing what B is. And then just assume for now that B is 1. So from the message that Alice sends to Bob, he has to be able to output psi. But on the other hand, if Bob received the 0, then from whatever Alice left at her place, she has to be able to produce psi. And so now just tell Alice it was 0 and tell Bob it was 1, and voila, they have made a copy of psi, which is impossible. And so indeed, this was a proof of Chandran et al. In 2010 that this was a secure, that the protocol that I just described is secure because this attacking game is not possible to achieve. Actually, I believed it for a while, but they actually made one big mistake, and that is that it can be actually attacked when Alice and Bob share some entanglement. And they actually didn't forget about entanglement. They reasoned that entanglement wasn't needed because it could be created in the first round by Alice sending sort of 1/2 of an EPR pair or whatever state they wanted to share to Bob, and then they have entanglement and they could play. But that's not quite right, and here's a way of attacking it, and I want to show this because it's kind of a cute attack. So it's teleportation, which we all probably know, but for those who don't, the idea is the following, that Alice and Bob share an EPR pair, and then Alice has an unknown qubit psi. She does a Bell measurement on psi and the half of the EPR pair, which results in 2 classical bits, C1 and C2. And then if she if she does that measurement and somehow it feels that instantaneously psi has been teleported to Bob, but it hasn't really been teleported like that, it has been perturbed. One of the 4 Pauli operations has been applied to it, and so from Bob's point of view, this really is a random qubit still. But when he receives this C1 and C2, he knows what Pauli was applied, and he can undo that to receive exactly psi. So this is what teleportation is. And here's how it's used to attack this protocol that I just shown to you. So Alice and Bob now share 2 EPR pairs that I've drawn here. And what Alice does, so the goal is that Alice receives psi, and Bob has a bit B. If B is 0, if B is 1, he has to be able to output psi. If B is 0, Alice has to be able to output psi. Here's the protocol, how they attack it. So Alice, first she does is she teleports psi to Bob. So that's what she does. And she gets 2 classical bits, C1 and C2, which she's going to copy and send, of course, to Bob. And now Bob does the following. Depending on his bit, if his bit B is 1, he just keeps this EPR pair. He does nothing more. If his bit is 0, he actually uses the second EPR pair to teleport it back to Alice. And so this is what they do. And this occurs, of course, instantaneously. And now they both send to each other all the correction terms, plus Bob's also sent the bit B that he received. So this is how they attack it. And now you can see that if the bit B is 1, then Bob can actually recover psi because he knows what C1 and C2 are, so he can actually undo the errors of teleportation and output psi. On the other hand, if the bit B is 0, you can see that Alice can take this doubly sort of error, doubly Pauli corrected psi, and undo the first Pauli's or the second Pauli's from the second teleportation. And then since she still has a copy of her own Pauli, she can also undo that and get psi back. And so in both cases, B0, B1, they are allowed, they can actually produce psi. So the protocol can be attacked with entanglement. Okay, so that's really cool. And then, of course, the hunt was on. Okay, so people thought this is just a quirk of this protocol, but there must be more complicated protocols that cannot be attacked. And so different schemes were proposed, actually, interestingly enough, also by Lau and Low, who were actually the inventors of the proof that showed that bit commitment and other cryptographic protocol is not possible. So they came with these schemes. But then actually in 2010, we showed that actually no matter what protocol you use, it can always be broken. I won't show the proof of that. But so we had a general no-go theorem. Oops. But that proof really was improved actually by Beji and Koenig about a year later. And then their proof uses an exponential number of EPR pairs to attack a game with n qubits. And actually we need a double exponential, but sort of they improved it to single exponential. But that's still a lot of entanglement needed to do that. And so sort of the hunt went on to the following question. We were not able to show that this exponential number of qubits were needed. We could only show that a linear amount of EPR pairs are needed. And so there is a huge gap between what we could prove was needed and what actually the best attacks used. And so question one that I looked at for quite some time is there a better lower bound? So can you improve this linear lower bound to exponential? And in particular, does there exist a protocol that requires a lot of EPR pairs to attack, but which in the honest case can be efficiently implemented? So this would be great if that's the case, but because that gives rise to actually a protocol that in practice could be used. And question two, if we found such a protocol, can you actually realize it experimentally? And so then you have to deal with imperfections and errors, photon loss, and all kinds of problems that occur there. And I'm not going to talk much about question two, but I can tell you that some experiments are underway and have been already completed. So this is also an active area of research now. But I'm going to focus on this question one. Does there exist a protocol that is easy to implement on the honest case, but requires a lot of entanglement if you want to attack it? And this, to my surprise, had lots of interesting connections to completely different fields, namely computational complexity, even classical cryptography, and also holography string theory. So I'm going to show you a little bit about that. So that ties in with the conference here. And even functional analysis, which I won't show, but it also has connection with that. So here's a protocol that we've been studying that's due to Kent, Monroe, and Spiller that sort of combines everything I've told you so far. So it starts with, again, a random qubit that's being sent to the prover. And alongside that qubit is sent a random string X of n bits. And the verifier 1 sends just a random string Y of n bits. And then the prover, upon receiving these three items, quickly computes f of xy, which is known to everyone and is sufficiently computable. And then if that is 0, or if that's 1, he routes on the qubit to verifier 1. And if it's 0, he routes it back. Right? So it's a a culmination of all the protocols you've seen so far. And so the question is, how hard is it to attack this? And so let's look at the attacking game for this protocol. And so Alice gets an input X and a random qubit, and Bob gets an input Y. So and by the way, we shouldn't forget that they share entanglement, because otherwise it's not interesting. So they share an entangled state. And then they send a message, a quantum message to each other. And then at the end of the day, if the function value f of xy is 1, Bob has to output psi. And if the function value is 0, Alice has to output psi. And the quantity I'm interested in, which I call E, is the minimum number of qubits needed for a shared quantum state so that Alice and Bob can achieve this. So that's what I'm after. And I want this to be high for easy Fs. Basically, that's my goal. Okay, so here I have this attacking game, and the question is there an F which is sort of efficient, or at all even, such that this entanglement measure is larger than polynomial? This is my main question that I want to focus on. And my own intuition, and I come from computer science and mathematics, my intuition is yes, such a function should certainly exist, because here's sort of my intuitive reasoning, and I don't have more than an intuitive reasoning, otherwise I would have shown this as a theorem, but I don't have the theorem. But my reasoning is the following. Sort of the qubit, this qubit that is starting in Alice's hands, has to be on the right side, namely Alice's side or Bob's side, before Alice knows, and also before Bob knows, what the side is the right side, right? Because they cannot compute f of xy without knowing both x and y. And so this somehow feels to me related to the space complexity, and that is the number of sort of memory cells that a computer needs to compute this function f of xy. And we did show that this is somewhat true, because we show that if this function f is computable with not too much space, logarithmic space, then actually the entanglement needed to attack this game is polynomial. So we showed at least that is something consistent with that. But the question is there a function f in P, so P means easily computable, that is not in log space, because otherwise it would have polynomial amount of entanglement. That requires a lot of entanglement to play this attacking game with. And sort of, I don't have I didn't prove anything definite with respect to this, because it's really difficult. And as you can see, it ties in here with questions about complexity theory. Namely, it's wide open whether P is actually different from log space. So whether there is a function f in P that is not in log space, that is even not known classically. So you see that it already ties in here with complexity theory. But the situation also ties in with other situations very similar, and these people didn't think about this quantum setting. In cryptography, one is called private simultaneous messages. Another one is conditional disclosure of secrets. I will talk about that a little bit later. Secret sharing, which is another notion in cryptography. And in all these settings that look very similar, the best upper bound known in these respective settings is exponential, and the best lower bound is linear. So these things have the same vibe, but it's not clear how it connects to this. And we will show it is connected. But first, there was this a bit of surprising connection, and this is actually why I'm giving this talk here to the ADS CFT correspondence, which was a bit of a strange thing for me, but I guess it's all known very well to most of you here, I assume. And it deals with this thing called anti-de Sitter space, which I guess you all know is a model of space-time used for theories of gravity. And then on the other hand, you have a conformal field theory, and this is one dimension lower. So we can think of this as a three-dimensional cylinder, and then sort of on the boundary is this conformal field theory, which is one dimension smaller, and there is this, and this is used, this is what it is, and there is this correspondence between these two that says any action, anything that happens inside the bulk here can be explained by this conformal field theory on the boundary. And it's called the bulk, and that's the boundary. And actually this is a tool that's been used not only to study models of space-time and theories of gravity, but also for black hole physics, quantum chromodynamics, and also for condensed matter physics. This is a tool that is very useful. So why am I saying this, and what has it to do with my cryptographic quantum position verification? And this is the connection, which was due to May and Dolev and Cree. So here we have this correspondence again. And now, if you think about it, you can implement an honest QPV protocol in this, if you could, in this anti-de Sitter space into this 3D space where I sort of depict it like here, sort of time goes, I guess, upward now, where we have the verifiers 0 and 1, in my case, sending stuff inside the block to the prover, and then the prover, upon receiving these things, sends something back outside to the boundary, or almost to the boundary. And since there is a correspondence, there is an explanation or a similar a way of doing things on the boundary. And if you squint at your eyes and think about it a little bit, you can see that this action then translates actually to a sort of an attack on this QPV protocol. And so what the ADS-CFT correspondence says is there is a, for every honest protocol that occurs here in the ADS side, the corresponding CFT explanation is an attack on that protocol. And so what these guys actually say is even more. They say that there actually is always a linear upper bound in the amount of entanglement. And this is even efficient. So they say that any honest protocol here can be attacked with a linear amount of entanglement, if this correspondence is true. And in particular, if f is in P, then this entanglement is really polynomial. It follows actually from the first point. But of course, there's no construction given. So they tell me, Harry, your protocols are not secure because of this correspondence, but we're not going to give you a way of breaking them. So I, of course, don't believe them. And there's lots of assumptions and unproven conjectures needed. But I think it's pretty interesting because there's a lot of tension here between, on the one hand, this ADS-CFT conjecture in this form, and the intuition of me, and not only me, but also of a lot of computer scientists, that actually these protocols that I showed you, there must be instantiations of F for which they are secure. How much time do I have? 4 minutes. Well, okay, so I'll raise a little bit to the last part. So this is sort of an interesting realization. And then we actually sat down with the people who work on this from the Stanford group, and they actually came over, and we had a very fruitful cooperation. And we started to look at not our F-routing protocol, so our position verification protocol, but at these other classical protocols that are around, to see if there is also a connection with the ADFC correspondence and that. And we actually did find that it is. And sort of the notion that we looked at is this conditional disclosure of secrets. It is very similar, although different. So Alice and Bob, it's classical. Alice and Bob have Alice has an input X and a secret bit S. Bob has a string Y, and they can share some random bits. And there's sort of a referee who both knows X and Y. And then there's a function f of x, y. And Alice and Bob send a message, depending on their inputs, to the referee. And the referee should learn only S if and only if this function is 1. And otherwise, he should have no knowledge on what that S is. So it's conditional disclosure of secret. So conditional on this function being 1, the referee learns what S is. That's what it's called. And of course, they're trying to minimize the size of mx and my to achieve this. And by the way, it is possible to always achieve this. Here's a little example, but let me sort of not show the example. And what they've shown with respect to this is that for any function f, there is an upper bound of 2 to the square root times log n. So it's sort of a little bit less than exponential what we had in our previous setting. And I'm not talking about this second point, but the lower bounds is that only linear lower bounds are known. So they have, again, a big separation. That's what you should take out. And what we did was we made a quantum version of this, what we call conditional disclosure of quantum secrets by just making this whole thing quantum, still keeping X and Y classical, but the secret is a quantum bit, and the messages that can be sent are qubits, and the shared random state is now a shared quantum state. And what we showed, and this is kind of what I want to say here, is that if you have a classical protocol that does conditional disclosure of secrets, then it implies that there is a quantum one, and more interestingly, a quantum version of this sort of classical primitive is equivalent to our F-routing game. So that's kind of very interesting, because this F-routing game, that came about from this quantum position verification protocols that we have. And now it turns out that that actually, if you look at that in the classical eyes, that is actually a sort of a notion that was studied by the cryptographers. So the cryptographers have a stake in this as well, as you can see. And I'm not going to show you the protocol, but it's kind of a nice, you need a few nice ideas from quantum information. So I'm skipping over this due to time constraints. And I want to sort of end by the following. So there's this consequences first, and that is actually surprising to me. For any function f, the entanglement needed to attack it has now been improved from exponential to this slightly sub-exponential bound, but still large. So that comes from really interesting techniques from the classical side. So they have now given a more efficient attack on the quantum side. We have this consequence that says if f is somehow slightly bigger than log space, then it still is polynomial time. It has polynomial entanglement to break it. But it's still completely open whether this ADF-CFT conjecture applies or not. So whether there exists a function f in P that has more than polynomial entanglement, or that everyone in P has a polynomial amount of entanglement. And even there's still a way out, even if the ADF-CFT correspondence is true, then it may still not imply an efficient, from a computational standpoint, attack. Maybe it doesn't need a lot of entanglement, but maybe to do the attack requires a lot of time. And so in this paper, we really had a lot of different connections. So here you see the things I talked about. So this quantum disclosure of secrets and F-routing. So this is the QPV thing, and then it sort of connects to a lot of other notions in cryptography as well. So this is like a nicely connected graph. And I sort of want to end with the following interesting thought. So we started out to come up with honest or good protocols for quantum position verification. And then we did our first inversion, and we sort of went into the mindset of Alice and Bob to attack these protocols. And so we were studying attacks on them. And then the second part, basically sort of also because of the cooperation with the ADF-CFT guys, we started to discover that if you had a very good attack on such a protocol, then that would lead to an efficient protocol in a quantum sense for this conditional disclosure of secrets. So now actually it's interesting, we get one or two things. We either get that this ADF-CFT conjecture doesn't apply, and we get a secure QPV protocol. But if we don't, then not all is lost, because that will then imply an efficient CDQS protocol. So one of these two things still happens. And this is sort of a reminiscence a little bit in complexity theory, where you want to have also, you want to prove good lower bounds, but you can actually prove good lower bounds by getting very good upper bounds for other complexity classes. So there's this nice interplay. Okay, so finishing up, and I think I'm right on time. Quantum position verification is not possible classically, not possible quantumly. We studied a really simple protocol, F-routing, and that had really lots of connections to complexity theory, cryptography, and even ADF-CFT conjecture, but many open problems remain. And it's also very interesting to realize there is a separate stream of research that actually tries to implement these ideas. Thank you.
All right, so we have time for a couple questions. In the meantime, I'm going to ask Czaslaw to come here. I don't know where Czaslaw is now. Perfect, I can start setting up. Yeah, first question, Rob? Oh yeah, sorry. Keep forgetting there's only one mic here.
Hi. Okay, thanks. Interesting talk, but I feel I'm just trying to understand one of the bottom lines. So I thought you said that, forgetting about ADS CFT, that if the function f is complicated enough, it's not in log space or something, that then the attackers need more than exponential resources and or more than polynomial resources. But then, did you also say that ADS CFT is saying that that's not correct and they need linear?
Yes, that's exactly what they claim, and I don't believe that. But
Okay, so in other words, so my question is this tension, I was going to say contradiction, is it resolved yet?
No, it's not.
It is not. Okay, that's what I wanted to get straight.
Yeah, no, and there's sort of an ongoing sort of conversation with them, and well, it's very friendly. I mean, we are on speaking terms.
Actually, one other thing. Sorry, if you're right, is ADS CFT wrong?
Yeah, well, and at least the form that they think is right, it's wrong. Yeah.
So it's that significant. If you're right, they're wrong.
I think so. Yeah.
Okay.
Yes.
Okay, so only if you promise it's going to be super fast. Okay.
Thank you. Really great talk, and I wasn't aware of all this work on this topic. So I'm not sure if I understand the generality of the strategy, because the most general protocol you presented was with quantum input on one side and classical on the other side. So it feels like there is space for having quantum inputs on both sides and output on both sides.
Yeah, very good. So the actual, I didn't show that, but the general no-go theorem takes that into account. And actually, we also have protocols that have both quantum from both sides coming in. So yeah, that is, of course, this is just one nice. Yes, no, very good. This is one protocol that we have sort of studied, and there's others where both quantum from both sides happens. Absolutely true.
All right, let's thank speaker again. Thank you very much.
It's actually mine, but
I will give you. 2 minutes.
God.
Don't be nervous.
Nobody here.
Can you go directly into
Yes, let's see.
It's fine, but this is sort of.
Yeah, no, it's fine. I can. I hope.
Yeah, no, it should work. It should work better.
All done.
You want me to give you the exact time or some time for questions?
Give me some time for questions, but.
Okay, so I'll tell you 10. When I tell you 10 minutes and 5 minutes, is.
So I have 30 minutes.
Yes,
you can give
I'll
me
give
10
you
minutes.
At 15, I'll give you 10.
No, 10. Give me 10, then I know I can
perfect.
maybe
So you
go
judge.
for until 5. Yeah.
All right, our next speaker is Czesław Brukner from Vienna, and Czesław's going to talk about what makes an observable invariance under quantum versus classical reference frames. Okay, Czesław, so who's this?
Thank you, and thanks the organizer for inviting me here. I'm going to talk about a couple of projects that are all around, definition of the observable in quantum reference frames, and this work has been done with Carlo Cepolaro, who is a PhD student in our group, Ali Akil is from Hong Kong, a postdoc, Pavel Czeslinsky is a PhD student from Gdańsk visiting us, and Anna-Katrin Delhamete and Victoria Kabel were PhD students. Now they are postdoc. Victoria is now with Flaminia in Zurich. So you already heard about the quantum reference frames, but I have to go also into a small introduction. The main idea of quantum reference frames is to extend the usual situation in a lab, if you want, in which you have some quantum systems maybe on some optical desk, and then usually to measure distances or maybe time intervals, you use some classical clocks and rulers. And now what we want to ask, what happens if instead of that we use rulers and clocks that have quantum feature, can be in a superposition entanglement, and then measure distances or relative distances between these objects by such quantum rulers. Of course, this is just a cartoon, and I will go into more details later. So, what is the content of this talk? I will say very briefly what I mean with the observable. Then I move into known cases when we have invariance on the classical reference frames transformation, generalize this to the quantum reference frame transformation, and then if time permits, I will say something about whether from inside the quantum reference frame we can learn something about global properties or global observables like a charge. It will be clear later on. So here is a definition of observable. So if we have a symmetry that is mathematized through the group transformation, then I will say that an observable O is a physical quantity that is invariant at the changes of classical reference frame, or if we don't talk about global reference frame, about coordinates, meaning that it is the same for all the observers related by this symmetry transformation of the theory. And what I mean this technically is that this observable preserves its form under the action of maybe unitary representation of the group. So here are simple examples. And I'm talking now about classical observables, maybe a classical system. So if we have an Euclidean translation invariant theory, then all what means, what has a physical meaning are relative distances. So we can have some gauge degrees of freedom, like absolute distance to some arbitrary origin of reference frame, which might be just imaginary. But what really physical has a meaning is the relative distance, and also we can build up out of this observable any function depending on this observable to get new observables. Now, if the symmetry changes, so also the observables. So when we move from a Euclidean translation invariant theory, something which is Lorentz invariant theory, then the previous observable, which was maybe the spatial relative distance, is not anymore an observable, but we have to find a new one which will be invariant under a new set of group transformation, like a Lorentzian distance between two events. This doesn't mean that you cannot measure relative distances at a given foliation. It just means that it will not be invariant, and you will see that actually this is just a special case when T1 and T2 are the same, and when you go into another reference frame, you will recognize what is actually observable, what is invariant under new group of transformations. So here is an example of a classical reference frame transformations. It's a translation, how we do it when we apply on a quantum object. We think about some state of a particle B, and I will keep this notation for the particle or for the object B, and I will move between different reference frames which are called C and A. So if I have a state given by in reference frame C, and then I move to A, which is whose origin is just shifted by XA, I need to apply this group transformation, namely generator of translation times in exponential times the distance between the two reference frames. And now in 2019 we move away from that, trying to generalize when we thought that we still keep a notion of reference frame, but the reference frame is, from this reference frame you can look at all possible systems external to it, including some system that may serve as a new reference frame. And so in that sense, we have something which is very similar to the previous case. If we think about this A system, a very well localized, almost classical reference frame, and then the transformation from one to another reference frame is very similar as before. You have this shift operator, but you should take care also about the cat of the previous reference frame, which now transform from XA into minus XA associate to the old reference frame. And if you require this transformation for all xa, then you recover the unitary transformation that can serve as the transformation to switch from one to another reference frame, which is just a control unitary. It reads out what x, where A system is, then shift B correspondingly, and then just permute with a minor side between A and C. And then you get this very strange phenomena in which something which is maybe where the all reference frame is in a superposition, once we move to it, the things get entangled that were not entangled in the previous reference frame. So let me say something about this transformation. This transformation in our original paper with Flaminia and Esteban was the idea really that we should not think about three systems per se. We never have this global picture from above. We are sitting already on C and look at the external system, and then we go to A and look at the other two. And therefore, this transformation is from the Hilbert space of AB to CB and gives certain then transformation for the phase variables. One transforming, for example, the distance to B into relative distance when we jump to A. Also this swap between A and C. And also the momenta are transformed as a canonical observables in that way. And maybe I just put some attention on the last one. You can think about that if you're sitting on C and you look at A and you have some momentum of A as seen from C, this momentum is exactly the same as the minus momentum of the rest if you would be sitting on A. So if you think that A and the rest have a total momentum 0, it's exactly what you expect here. Okay, so now let's move to definition of the invariance and the quantum reference frame transformation. In the presence of, I would say now, quantum control symmetry, under inverted commas, an observable O is again a physical quantity that is now invariant under quantum control changes of classical reference frame coordinates. So again, we have an observable that takes the same functional form of the phase variables, just like one before changing the reference frame, with the change of the labels between A and C. And the type of the transformation that I will use here is exactly the generalization of the thing that I showed for translation, namely that I have this quantum controlled unitary application for the group G, which indeed in this paper has been generalized from translations to all Lie groups, compact Lie groups. So here's an example of something which is rather trivial, is when we move from one reference to another, we have a relative distance operator which is invariant under quantum control translations. Now, already this relatively trivial case gives some insights, and insights in the sense that some Hamiltonians, for example, in Newtonian limit of gravity, depends only on the relative distances. And we see that this Hamiltonian, in the case where we think about a large mass in a superposition, can transform the situation in the upper left corner into the lower left corner, in which I now don't have ABC, but I have other notation for this case, where we can, this situation which space-time is in a superposition can transform in the known situation in which we classify space-time, and then see other systems are entangled or in a superposition, and we can solve this problem. So even to say that an observable which is a relative distance and which is understandable is invariant under quantum reference frames transformation gives you something valuable in a sense of transforming unknown physical situation or physical situation that we do not have a consensus how to deal with into the known one. And what behind is so-called general covariance principle, namely that if we have an equivalent situation as seen from different reference frames, then we don't need to choose any of them in any particularly, and the physics will be the same. So here we have a situation, if we have a large mass localized and a small mass in the superposition, and the same situation from the point of view of the small mass. And in both cases, what we will observe is that things that are in superposition will start to go towards the localized mass in both pictures, and we have the same physical phenomenon. But these things is not covariant. In other theories, these situations can give very different predictions, like the collapse models, in which in the lower picture we have a localized mass, and we know that then there is nothing to collapse for the small mass. So the small mass will tend towards the large mass in these two amplitudes in the superposition, while in the other reference frame in which the small mass is localized, because the collapse models imply that the large mass should collapse, will lead to one or the other situation, which is provable distinct in physical consequences in these two pictures. And the same is for the semi-classical gravity, namely, in the lower picture we will have the same thing, because the source is now of gravity the mean value of the gravitational field. So here is a localized, and we have a small mass towards the large mass. But in the upper picture, if we keep, for example, these masses on a distance, for example, in the traps, the small mass will feel no force and will not be attracted towards the large mass. So we have seen that even finding relatively simple observables like a relative distance can have implications for our understanding of even some alternative paths to the theory of gravity. And what we have seen is a trivial observation. Namely, it seems like if an observable is invariant on the classical reference frame transformations, which is the case of the relative distance, it seems that it's also invariant on the quantum reference frame transformation, and by some branch-by-branch argument. It's very much in the spirit of many worlds, which I'm not advocating, but you can think about that. And now the question is this always true? Is this always the case? And what I want to say next is that it's not the case. It's obvious that something which is invariant on the quantum reference frame transformation should be also invariant on the classical reference frame transformation, because they are the special case of the quantum reference frame transformations. But the other way does not need to be necessarily true. Now, in order to show this one example, I have to extend the notion of observable from something which is a common understanding of observable related to the single-shot experiment into something what I will call is observable for n copies when n goes to infinity. So it's a very unusual observable. So what I mean with this is, for the case, for example, here of spin, that I have n copies all equally prepared. And then what I can introduce is so-called frequency operator. The frequency operator is something which basically counts how many ones as you have in a sequence of n copies. If you measure, for example, spin up and spin down, you have a just two-level system. It can be, of course, generalized to d-dimensional system. So what you have here is an observable that measures how many ones over n you have. And this is now a highly degenerative projector on this case, which is the sum of all these combinations of projectors, the sum over all permutation of these projectors, where k times you have 1 and n minus k times you get 0. Now, this frequency operator has an eigenvalue eigenstate in the limit of n goes to infinity. And it turns out, due to Finkelstein, Hartley, and Herburg theorem, that the probabilities as given by the Born rule, so this is a Born rule, the probability to get the outcome 1, is actually the eigenvalue of this frequency operator in the limit when you have infinitely many copies. So in that sense, the frequency operator is an observable, and in the limit of n, it tends exactly to the probabilities. This is nothing new, of course. In order to find out probabilities, you have to repeat many, many times the measurement, and this tells you just if you go into the limit of n, your outcome will be a probability. So you can think in that way that for n copies, the observable is probability or any function of probability. like maybe Shannon entropy for this measurement setting, and so on. Now I'm coming back to now the initial question. The initial question was, can we find some observables that are invariant under quantum reference frames, but not classical reference frame? Now, let's look first at the classical reference frame. And I introduce an observable, which is now a function of probabilities, which is defined as a coherence, some measure of coherence. This is so-called entropy of coherence, which is the difference between the von Neumann entropy of a diagonalized state, rho, so it's a diagonal part, or the full rho. So it measures how strong are off-diagonal elements. It measures how strong is the coherence. Now it turns out that this coherence is invariant under classical reference frame transformations. Now, it's obvious that it's invariant. You just moved your reference frame, the coherence is not touched. Now, if you think about quantum reference frame transformation, then it's not anymore invariant. And this is apparent from the picture because some, for example, coherence will be transformed in entanglement. Things about, you can see either on A or B. So what we have seen here, that individually, coherence and entanglement are not invariant on quantum reference frame transformation. And for entanglement, I also use, for example, just von Neumann entropy of the reduced density matrix. So we see that by moving from C to A reference frame, neither coherence nor entanglement is preserved. Well, here is basically the main message. If we move to a new quantity, which we call coherence plus entanglement, some of those, in terms of the entropy of coherence and von Neumann entropy, we can add them up and see that this will be invariant under this quantum reference frame transformation. And in these extreme cases, is almost visible that what is the amount of coherence in A will be somehow transformed into entanglement between C and B in the second reference frame. So we found something which is invariant under quantum reference frame transformation, but the things that were before that, like classical reference frame transformation, in coherence and entanglement were not anymore invariant. So now, this is not the only measure of the two that can be invariant under quantum reference frame transformation. Namely, if you combine the so-called norm 2 measures, then you can think about linear entropy and also norm 2 measures for the coherence, and you will see again that these two in the sum are invariant under quantum reference frame transformation. However, this might give you an impression that you can add any two measures of the two, and this is not true. So if you, for example, choose us to norm 1, so if you don't have here 2 but not 1, and then, for example, add to that the von Neumann entropy, this will not be invariant under quantum reference frame transformation. And here is the reason why this may be is true, that for some measures of information you have the invariance and for the others not. And that's the sketch of the proof. Namely, if you think about the two values for the entropy of coherence and entanglement entropy, in both before and after moving to the new reference frames transformation, the result is the von Neumann entropy of diagonalized state. So if one proved that diagonal density matrix are the same up to the permutation of these two systems seen from C and A, then we have the proof of invariance. And in order to see this, it's quite easy. Namely, you can think about all diagonal elements of the density matrix of A with respect to C and the C with respect to A, and you can enumerate them or summarize in these sets. And now you can think about the diagonal element of the first one which you can get by tracing out other degrees of freedom, the degrees of freedom of B, then you apply quantum reference frame transformation and see how this looks like from the C point of view. This unitary transformation from one to another, still tracing out over B degrees of freedom. And then you see that if you think that this is a group element, this will correspond to another group element, H, because we sum over all group elements, so it doesn't matter whether we multiply this. So at the end, we will end up with another diagonal element of the second density matrix, but since we are interested in all elements, certainly these element also belongs to the set of all diagonal elements. And therefore, we see that these two sets are basically invariant, and the whole quantum reference frame transformation is just permutation of diagonal elements, meaning that the whole sets of diagonal elements are both the same in two cases, and therefore we have the invariance of the sum of the coherence and entanglement. Now, one can ask oneself, is this a very general statement? Because we see that for some measures of coherence entanglement, we do have invariance, for the other don't. How should we understand this? And I would like to go back to the similar situation as we had at the beginning of the talk. We see that there are some measures, very different measures of coherence entanglement that are all invariant under classical reference frame transformation, and then there are only particular measures that we have to choose that in the sum give invariance on the quantum reference frame transformation. So this is very similar to the situation when we think going from one group to a larger group of transformation. In Euclidean spatial translation, we have the relative distance, also some weird function of this relative distance that would be all invariant under Euclidean spatial translation. But once we go to the Lorentz group, we have to pick up a very particular quadratic, if you want, measure of distance in order to get a new invariance under a larger group of symmetry. So I would claim that the quantifiers that yield the invariant observable in the sum reflect the symmetry of the problem, and that's something which we should take care of as an embrace, in a sense, and not see as a shortcoming that not all of them are invariant. Now, I'm coming to the end of my talk, and I want to say just one last thing. This slide you have seen. That's change from from C to A reference frame by quantum control translations. And I want to remind you that this framework that we built up in 2019 is actually equivalent to the framework of the perspective neutral approach. And the perspective neutral approach starts from the gauge constraint and has this kind of bird view on all three systems from above. So all three systems are there, and put some gauge constraint which tells you that the sum of three momenta is zero, so it's a zero charge constraint, from which then by certain set of reduction maps one can add one can come into the perspective dependent framework, which was the starting point of our framework. And from that, one can then derive what is the unitary transformation, moving from one to another. And so the question is that I want to pose first, how one can extend this framework to non-zero charges. And this one can relatively easily do in both approaches. And what the resulting thing will be that the unitary transformation is slightly changed with this minus p. And now the question is also related to observables in somewhat different way. The question is whether the parties in individual perspectives can learn the global charge. This doesn't seem very possible because it concerns something about three of the systems altogether, although in each perspective individually, externally you have just two systems. And the idea is that you have a lot of systems prepared which are all identical, just seen differently from different reference frames. And when you have a sufficiently set, many these states, a complete set, what you can do, you can then have so many set of states that you can determine the entire unitary transformation by communicating the results of your measurements among yourself. So if we think about the cleave collecting many information about this state, and Alice collecting many information about this set of states, by communicating the results, they can arrive at the unitary transformation between these two sets of states. That's a classical communication, and arrive and determine the entire unitary transformation that transforms from one frame to another, and of course then also get the information about the charge. Okay, with this I would like to thank you. I have the two major things that I wanted to share with you. Observables invariant and the quantum reference frame transformation may not be invariant at the classical reference frame transformations. Coherence plus entanglement. Which other single copy observables may have this feature will be very interesting. Can one find the charge of the state from the measurements within local quantum reference frame was one of the questions, and I would like to see how we can extend this also to the states of superposition of charges, at least in those cases where there are no super selection rules, like in a momentum case. With this, I would like to thank you for your attention.
All right, we have time for some questions. I see one hand, two hands, three hands. Well, you can go. That's okay.
Thanks a lot for a beautiful talk. I have a question on the proof you have shown for this invariance of coherence and entanglement. You've said that you can only do it for the entropy and the 2 entropy, but would it be possible that for other values there is an inequality instead of an equality?
Yeah, sorry. Yes, you're right. There are in the paper indeed proofs that there are inequalities with slight, I think, weak assumptions, namely that in the extreme cases you have to get 0 and 1 or 1 and 0 for the 2, then you can get inequalities. That's one thing. And the other thing, what I want to say is that the proof to me suggests that if you use comparable map, the same measures or same type of the measures for both of them, you should get invariance. So this was case both from the entropic one, but also for the quadratic norms. And if you go even to p norms, which we haven't looked up, I think you should get the same, because it's really just about permutation of the diagonal elements, and there, if you take the same function of this, it should be the same.
Yeah, hi, thanks, Czeslaw. So this looks like it all implicitly presupposes flat space for these symmetries, and I mean, will anything significantly change for a constant curvature space or more general curve space?
Yeah, we have also papers when going beyond flat space times. I would not know about invariances to say something that's very abstract. It's about superposition entanglement. I would not know how even to extend to these groups. But I don't think it's anything particular about flat space-time. Yeah.
But will the invariance?
Okay.
Yeah. Thanks a lot for the talk. I was wondering if you had any intuition as to whether this also works for observables in the quantum mechanical sense of self-adjoint operators.
Yeah. That's what I will call a single copy observables. I don't know. I think. Okay, so the only what I can see so far is whenever you write the state from within one reference frame, you write in some basis. This is the basis on which you apply this group of transformation. Then you have the, so to say, trivial observables, like a relative distance. That's obvious. Then the only what is remaining is to have something with a phase, which will be some kind of momentum. And what I wanted here to show that that I don't think that anything which is a momentum as measured by one reference frame will be invariant, because this is simply just a part of the system. But nevertheless, you can say something about momentum of the entire three-partitive system by combining the knowledge, individual knowledge about the momenta in reference frame. So I think then I'm not sure, yeah, but at least this example shows that if you elevate yourself and look from above, you can say something more than just about trivial observables.
Okay, let's thank the speaker again. Thank you, Czeslaw. Nice. Do you have the mic to put on?
I remember for this thing, you should not
All right, so our next speaker is Kempf from the University of Waterloo, and he's going to talk about generalized another, the metric from energy momentum non-conservation. Achim, the floor is yours.
Andrew, should I take another microphone?
Oh, yes, thank you.
Okay. Hello, thanks for coming. So I will talk today about generalizing Noether and other things, but this is the headliner. Let us remember a special case of Noether's theorem. If the metric is translation symmetric in space and time, then we have energy and momentum conservation. I'd like to go beyond that, so that we see that if the metric is generic, doesn't have any killing vector fields, then there is no energy momentum conservation, and vice versa. At this point you might think, okay, we knew that, right? So what is actually new here? And what's new here is that I'm saying that if you know the details of the non-conservation, you can reconstruct the metric. So if you have just how energy conservation is violated, momentum conservation is violated, that actually tells you the metric. As a special case, you get regular Noether, of course. If energy momentum is conserved, you get space-time translation invariance. Okay, so what's needed to do this? What's needed, by this I mean we want to show that given a generic metric, we can derive the energy momentum non-conservation. That's trivial. We do that. But from the energy momentum non-conservation, we get the metric. And if you think of it, this is all about space-time. Very local stuff. What is the curvature here? What is the curvature there? This is energy momentum. And we know from quantum theory that that's very non-local. It's as if this was a Fourier transform. Right? If these two sides are equivalent, it's just like a Fourier transform is an equivalent. So what we are looking for is a Fourier theory of geometry itself, not just of functions that live somewhere, but of geometry itself. There has been in the literature, for more than 100 years now, an attempt at doing something like that. It wasn't formulated in this way, but effectively that's what it tries to do. That's the field of spectral geometry. Let me remind you of spectral geometry. Spectral geometry goes back to Hermann Weil, who in, I think, 1904, considered the case of, let's say you have a metal sheet, a thin metal sheet in the form of the surface of a potato. And you take a spoon to it, and you ding it a bit. Then it will start vibrating. And you can record the resonance frequencies. And clearly, the shape of the potato will determine what the sound is that you get out of it, what the frequency spectrum is. And Weil asked, if you only hear it, but you don't see it, from the frequencies alone, can you infer what the shape of the object was? Of course, not just in 2 dimensions, we want to do that in n dimensions, and also for space-time. This is in its own right a mathematical discipline, spectral geometry, which I think is attractive in its own right, because it combines the mathematics of general relativity, differential geometry to describe shapes, with the mathematics of quantum theory, functional analysis, spectra. Now, if we want a theory of quantum gravity, not only will gravity and quantum theory come together, but also the mathematics of gravity will need to come together with the mathematics of quantum theory. So differential geometry and functional analysis will somehow need to be combined. And that is a kind of Fourier theory of geometry, because we would capture, if this works, we would capture the shape of things, the geometry of things, in terms of just a spectrum. You know, when you listen to a vibrating object, what you hear doesn't depend on what coordinate system somebody paints on that object. The spectrum consists of geometric invariance. So if we could do this, this would be very helpful for quantum gravity, because we wouldn't have to mod out the diffeomorphism group. It's modded out already. It would give us a coordinate-free formulation of geometry. Okay. It would give us a coordinate-free description of geometry. However, there's always a but, it is known that the spectrum of, let's say, the D'Alembertian or Laplacian or whatever wave operator does not contain enough geometric information to encode the geometry completely. You get some information, but not all of it. So if that's so, should we just give up on this? No. I have something new to say about this, which is that spectral geometry does work. We can make it work, what Hermann Weil wanted, namely that we can hear the shape. We can make that work, and not just in 2 dimensions, in any number of dimensions, and any signatures of the metric as well, so for Lorentzian manifolds as well. Of course, you have to do something extra. And what that extra is that you take, in the case of the potato with the metal sheet surface, you don't just ding it a little bit with a spoon. No, you have to hit it hard too. And then it's sufficient. And why would that be? Well, it's because if you excite the vibrations of the manifold strongly enough so that the oscillations get into the nonlinear regime, then the modes will start interacting with each other. Like in the 5^4 theory, where different modes start interacting with each other. Particles will scatter, right? And in the case of sound waves on a metal sheet potato, same thing. If the oscillations are strong enough, the modes, these harmonic oscillators, will start to couple to each other. And that means that if you excite, let's say, 2 of the resonance frequencies strongly enough, large enough amplitude, they will excite other resonance frequencies as well. And you can hear that. And just before, what you hear does not depend on what coordinate system anybody painted onto that potato. So it is all spectral, it's all geometric invariance. It's all geometric invariance. The original spectrum, but also how the various modes are interacting with each other. If you excite those frequencies very strongly, what other frequencies get excited with it? So what I'm proposing is to generalize spectral geometry to make it nonlinear. The first step, as I said, is we tap the object lightly. As a consequence, we hear the spectrum. We obtain, therefore, the propagator or the wave operator in its eigenspectrum. We obtain the spectrum of the wave operator. The propagator is a right inverse of it, so it also inherits the inverse of these eigenvalues. So if we tap lightly, we can write down what the propagator is, we can write down what the wave operator is, just from listening to what's going on. We can write them down, but only in their eigenbasis. It's diagonal, we just write those frequencies that we hear, we write them onto the diagonal. In the case of quantum field theory, when we don't talk about the potato surface, but the curvature of space-time, then it's just free particles. We're looking at the particle spectrum. But then we also tap strongly. In the case of the potato, we take a loudspeaker and we blast 2 of the resonance frequencies, for example, and very loudly, so that our potato starts vibrating so strongly that the amplitudes are so large that we get into the nonlinear regime. We can, for example, describe what's going on the potato through a 5^4 theory. It's not such a bad model for what goes on when you have a vibrating object and you enter into the nonlinear regime. So when you do that, when you excite some 2 resonance frequencies and other resonance frequencies will also be co-excited with that, you take a record of that. Oh, I excite this and that frequency, those others go along with it, get excited with it. What is the quantum field theoretic analog of that? If I quantize this, if I'm considering fields like a 5^4 field on a curved space-time, well, the second step, the strongly tapping step, is the step where the particles start interacting. Right? It's exactly the nonlinear terms in an action. I mean, the higher than quadratic terms in an interaction. In the equations of motion, anything that's nonlinear describes something that doesn't obey the superposition principle. It means if the equation of motion is nonlinear, the sum of 2 solutions isn't a solution, you have that particles scatter off each other. Right? So nonlinearities are particle scatterings. So acoustically, it's just that standing waves on the potato are interacting with each other and exciting other standing waves. In quantum field theory, it's particles interacting with each other. And what is it in the case of particles that we are measuring then? For the potato, it was just, oh, I excite these and these frequencies, and other frequencies get co-excited with that. In quantum field theory and curved space-time, it's just the S-matrix elements, right? We are measuring what happens if I smash this particle and that particle into each other, and then other particles come out of this. It's the same thing, just the quantum field theoretical version of it. All right, so now we've collected this information here, and if you think about our metal potato, it's all spectrally invariant information. It's all geometrically invariant information. It doesn't depend on any coordinate system. And now in the third step, what we do is we generalize the 4 vertex. We generalize the 4 vertex. Why would we want to do that? And what does it mean? See, much has been made of the fact that in quantum field theory, there is no position operator. Too bad that we don't have a position operator in quantum field theory. In quantum mechanics, in first quantization, it's very useful. If we want a position representation, we diagonalize the position operator, right? In quantum field theory, what the heck is the analog of that? Well, there is a simple analog. It's the vertex. We can diagonalize the vertex. It is diagonal exactly in positional representations, right? Because the vertex is local. Only if all 4 entries, all 4 parameters of a 4 vertex, all 4 ingoing legs are at the same location, is the vertex non-zero in a position representation. In any other representation, the vertex is not diagonal. Of course, this is not the diagonalization of a regular operator I'm talking about, because the 4 vertex is a 4 tensor. So we're talking about 4 tensor diagonalization, which is not unique. And it shouldn't be, because there are many position representations. Any diagonalization of a 4 vertex gives you a coordinate system. It gives you a positional basis. So what we do is, having captured the information, as I said, you irradiate your potato with 2 frequencies, and you get other frequencies excited as well because of the nonlinearities. In quantum field theory, we smash particles into each other. What we find is the 4 vertex, right? We get the scattering matrices. But we get the scattering matrix in the eigenbasis of the wave operator, because it's like the S matrix. We have plane waves, or what the curved space generalization of that is. We have plane waves going in, and then there's some scattering going on, and then plane waves, or the generalization of that, the eigenfunctions to the wave operator going out again. But by diagonalizing the 4 vertex, we get positional representations. We find out in the space of fields bases, which are position bases in which the 4 vertex is diagonal. So we can see, oh, this is a local interaction. And when we do that, the diagonalization has a tremendous benefit, because once we diagonalize the 4 vertex, we can move from the eigenbasis of the wave operator, in which we hear everything, to a position basis, which means we can take our propagator, of which we knew only its form in its eigenbasis, and write it as a Feynman propagator as a function of x and y. But now we've won, because once we know what the propagator is in a position representation, from that we can calculate the metric. This is the result of almost 10 years ago, and it goes back to the fact that when you have the Feynman propagator, you know that it scales in a particular way in the coincidence limit as a function of the Singh geodesic distance function. And from that, if you know the metric, if you know infinitesimal distances, you can derive the metric. Maybe that was a little fast, so I have another slide on this. So the metric is calculable from the Feynman propagator. It's an old result, but let me just quickly explain why this happens. The propagator diverges on light cones, which means the propagator tells us at every event in space-time where the light cones are. And if you remember from the book of Hawking and Ellis, if you know at every event in space-time where the light cones are, you can derive what the metric is up to a conformal factor. And it so turns out that the propagator not only tells us where the light cones are, but because of this scaling behavior that it has near to the light cone, it also tells us what the conformal prefactor is. And in fact, ChatGPT can also derive this, so I will not give you the derivation of it. It takes a few minutes and it can do that. All right, so here you get the metric as an expression in terms of the two-point correlator. This means that space-times are expressible not only as a differentiable manifold plus a metric, but you can express a space-time also as a differentiable manifold and a Feynman propagator. Same amount of information. If you have this, but not that, never mind. This describes everything, because from the two-point correlator, you can get what the metric is. So what we obtain then is a completion of the program of Hermann Weil, who asked, does the sound of a vibrating manifold tell its shape? And yes, it does. If you tap the manifold loudly enough, if you make it vibrate loudly enough. So enough so that you can hear the onset of the anharmonicities. So again, the first step is you measure the harmonic spectrum by tapping it lightly, and then you drive it at the resonance frequencies, at some resonance frequencies, loud enough to be able to record the additional frequencies that are being generated, and you collect that information in a scattering matrix, because it's a scattering matrix for quantum field theory. It's just listening to reverberations in the case of the acoustic potato. And in quantum field theory, what this means is, in quantum field theory on curved space-time, this means that to measure the energy momentum non-conservation in the S matrix, right? Because if you are working on a curved space-time, energy momentum is not conserved. And this means also, in particular, that when you scatter particles of each other, it's not the case that the outgoing energy momentum is the same as the ingoing one, because you have energy momentum non-conservation because of no symmetries. But we can now go further. Having measured the S matrix and all of the energy momentum conservation violations that are encoded in there in detail, we can take this scattering matrix, diagonalize it to obtain a coordinate system. Any diagonalization provides a coordinate system because it provides a positional basis. And then we can express the propagator that we obtained from measuring the harmonic spectrum in that basis. And then from the propagator, we can obtain the metric, and so we get the shape of the space-time, the curvature of space-time. So this generalizes Noether then, so that I suppose Weil might be happy. How much time do I still have?
13 minutes.
How much?
13? Well.
Oh, great. Okay, good.
12.
Okay. So what do we obtain then? We obtain that we can write quantum field theory on a curved space-time without using coordinates, in a coordinate-free way. So we don't need to worry about diffeomorphisms, for example. And why is that? Well, we saw that not only matter, in what I said earlier, that not only matter can be described by correlation functions. I mean, that matter can be described by the endpoint correlators in quantum field theory. That's what quantum field theory is about. It describes the motion of matter, right? So the matter can be described, of course, in terms of endpoint correlation functions in quantum field theory, but also space-time can be described in terms of these correlation functions. These correlation functions are not only impacted by curvature of space-time, no, they know all about the curvature of space-time. If you just know the correlation functions, you can calculate the metric from that. You just diagonalize the vertices and then write the propagator in the position basis, which you obtain by diagonalizing the vertices. And then once you have that, then we have this formula that I showed you to get the metric. But what it also tells us is that instead of writing these endpoint correlators in a position basis or in a sort of energy momentum basis in the sense of the basis that diagonalizes the wave operator, we can write our correlators in whatever basis we want. It's not just position and momentum basis, intuitively speaking. No, after all, these are just operators. In this case, a 4-valent one, a 4-tensor. It's just an operator. These correlation functions are just operators acting on the space of fields. For example, the space of fields that we are path integrating over in the quantum field theoretical path integral. So therefore, fundamentally, just like in quantum mechanics, the position operator isn't just multiplication with x. The momentum operator isn't just minus IH bar d by dx. No, they can take very different forms in different bases. The position operator is an operator, an abstract operator, which takes concrete forms in concrete representations. And the momentum operator is an abstract operator, which takes different forms in different representations. And so similarly, these correlation functions, functions, are really correlation operators, which take concrete forms in concrete representations, like a position representation, or an energy momentum representation, or any other representation. So fundamentally, these GN are just abstract operators. And from them, we can recover the whole thing in quantum field theory in a curved space-time. If we want to, we just take the vertices, diagonalize them, they're just abstract operators, we just find the diagonalizing basis, and then once we have that, we have a coordinate system, and we write the 2-point correlator, the Weilenmann propagator, in that basis, and then we use the formula to get the metric, and we get everything this way. But fundamentally, we have described quantum field theory, the matter part, and the space-time part simply as this bunch of operators here which act on fields. The fields that we sum over in the path integral. And that's a description which doesn't care about diffeomorphism, right? It's not bound to any coordinate system. And what can we gain from that? Isn't that just an abstract reformulation of what we knew already? Yes, but it can do more than that. It can do more because, you see, these GN, these abstract correlation operators, normally in quantum field theory, they have this property that all the vertices can be jointly diagonalized. Mathematics doesn't dictate that. If you have electromagnetism and the weak interaction, strong interaction, and so on, in principle, there's no reason that they all should be local interactions in the same basis, right? It could be that the vertex of one interaction is diagonal in a basis in which the other one isn't. Nature doesn't do it, but the math would allow it, and that math would allow it. Or you could have, and that might be more realistic, you could have that these vertices are diagonalizable only in some regimes, and in others they aren't. So in some regimes, you get a space-time representation, as we discussed. In some other energy regimes, you don't. So for example, you can have the situation where in a, let's call it a low energy regime, the vertices, that is to say the correlation operators for n larger than 2, are approximately diagonalizable, and then we can go through this program and we can write everything as quantum field theoretical correlators on a curved space-time. But it can happen that at increasing energies, these vertices either are not diagonalizable or they are diagonalizable, but now you find that your coordinate systems have different dimensions. It could be that, yes, it can be represented as quantum field theoretic correlators on a curved space-time, but maybe a different number of space-time dimensions. And in a very high energy regime, like the Planckian regime, it can happen, that by that I mean the math allows it, that these vertices are just not diagonalizable in any good approximation. In this case, it's sort of a pre-geometric regime. You can still do all the math. You have your operator, you can do calculations. It's just that it cannot be represented as quantum field theoretical correlators living on a curved space-time. So in that sense, the whole edifice of having a space-time stage on which matter lives is transcended. It's just a special case where these can all be diagonalized together. So this could serve them, as a model for the emergence of space-time and matter. And in work with Markus Reitz and Barbara Schroeder, we carried that further, and that appeared, thank you, that appeared in this paper here. At the time, we didn't know yet how to do the diagonalization of the vertices so that we actually explicitly then get the metric, but we were able to calculate other things that are not local. We were able to calculate the volume of the space-time and the number of degrees of freedom in there and the dimension of the space-time. So that was this PRL of 2 years ago. Then, on the whole, what we've seen here is that not only the matter, but also the space-time itself is fully encoded if you know, fully encoded in those endpoint correlation operators. And all those endpoint correlation operators, we know, because we often do this, just not as abstractly as this, we can collect them all in what is called the partition function. Right? That's just the usual partition function. And we know that the partition function is technically the Fourier transform of the e to the power I times the classical action. If you've not looked at the path integral like this before, have a look. The path integral is simply saying that the partition function is the functional Fourier transform of e to the power is. This is the Fourier factor, e to the power I times j phi. Right? But this also tells us that the path integral is an invertible thing. You can go from the classical action to the partition function, but you could do a partition function of this, e to the power I times the effective action, and view it like this and do a path integral of that, and it would get you back to here, modulo regularization issues. Quantization is a Fourier transform. If you do the stationary phase approximation of that, you get the Legendre transform, and you get the classical theory. People don't usually look at it this way, but it's just a fact. Okay, so what we see here is that these correlators, which encode both matter and the space-time, just together form the partition function. And then we can study that underlying theory, which may or may not have a representation in terms of quantum field theoretical propagators in curved space-time. We can study that either on the left-hand side, either on the left-hand side or on the right-hand side. This would be the usual way to study it, to say, oh, yes, we have the classical action and then we quantize it. But we could also say, no, we start with this. These are the basic building blocks, the correlators, because from them directly we get the space-time, directly we get the interactions. And of what kind of nature are they? We know what these things are from, right? The classical action, we know what that is built up from. We have here masses and all sorts of charges, and we have, the usual quantities that we care about in particle physics. What do we have here? Here we have only one kind of thing, and that's information, right? Because these are correlators. And for n equal 1, what is the n equal 1 correlation function? That's just a probability distribution. This is where von Neumann entropies, Rényi entropies, and so on live. The 2-point correlators they are all about mutual information, coherent information, classical and quantum channel capacities, entanglement as measured in negativities, and so on. Now for n equals 3 and 4, we get vertices, and what are they? They are information theoretically, just a higher order web of informational relationships, multipartite entanglement, and so on. So in a way, if we adopt the view that these are primary, then we just automatically have an information theoretic description of what's going on. And you might wonder, why would information theory be so fundamental? I know I'm preaching to the choir here. We all think that information theory is pretty important, but the way I see it is, the reason is that the notion of information is applicable even in the most counterintuitive regimes. If we go to a regime so extreme that we don't have a representation in terms of quantum fields that live on a curved space-time, there is no space-time, there is no matter, we just have these correlators and they cannot be represented anymore as quantum field theoretical correlators on a curved space-time. Even in those regimes where space-time dissolves, so to speak, the notion of it dissolves, we can still ask, how much information? How much information to describe this? How much information to describe that? How does the information get processed? So the notion of information is just more flexible, it's more applicable. To measure length in meters requires a reference meter piece, right? But we don't have reference meter pieces that are like 10 to the minus 25 meters long. But the fundamental unit of information is the bit or the qubit, and they always make sense. So I'm advocating here for even more of an information theoretic point of view. Thank you very much.
To answer questions? Okay. All right, thank you very much. As you can see, so I'm going to do 1, 2, 3, and I would ask you 4. I would ask you to be really brief and no follow-up questions. That's what the coffee breaks is for. All right. So let's begin. I'm excited to see the order. I'm going to begin by distance.
So it's a very nice speech about how this mathematical formulation of like GR and quantum theory and differential geometry and functional analysis show up in this idea, right? But now you're pushing this to the nonlinear regime on the functional analysis side. So say that you really develop this whole program and you get see a theory of quantum gravity where you can really describe this emergent spacetime. Would you expect this to also include nonlinearities in quantum mechanics in the sense that the part of the mathematics that handles that side would now be pushed to this nonlinear regime?
Yes and no. I don't think that, you see, when I speak of nonlinearities, I don't mean nonlinearities in the sense of violating this linear superposition principle of quantum mechanics itself, states. Instead, I just mean the nonlinearities. All right. Instead, I just mean the nonlinearities that describe interactions between particles, right? On the other hand, in the regime where we lose representability of the whole framework as quantum field theoretical correlators on a curved space-time, in that regime, we might also lose the probabilistic interpretation of the whole thing, right? Because even the probabilistic interpretation of it might be a representation-dependent thing. It could be that the same mathematical structure can be represented with so many space-time dimensions, with such a field content, or with so many space-time dimensions with another field content, like ADS-CFT could be a special case. It could also be that it has another representation in which there is no space-time, there is no matter, it's something else, and it doesn't even have a probabilistic representation. So it's just that we have abstract correlators. It's really just structure, right? It's a partition function, abstract partition function, full of nonlinearities, and how that can be represented. There might be equivalent representations that to us would look very different. And in that sense, since the probability interpretation would break down, the linearity of the probability interpretation of ordinary first quantization would also break down.
Yes, there is something that baffles me. You are in a compact space, and then your reconstruction will not work because the spectrum of the Lambertian will be continuous. So yes. You'll have to put density. Then
I know what you mean.
The mathematics is not under control.
Fedele, I know what you mean. If I was to do only what Weil intended, namely just listen to the spectrum, then it would be hopeless because a continuous spectrum doesn't carry information. But it's fine if the spectrum is continuous. The reason is that the interactions carry way more information. They allow you to then go into a positional representation and then you write your propagator in the positional representation and you do get the metric. You don't even need the spectral information in this case. You just need, it's much more rich to listen how modes excite each other than just listen to what spectrum they have.
You can continue. Hi Achim. Fantastic talk. A couple of questions. How much does this depend on the initial state? Do you need a Gaussian initial state? What are the conditions on the sort of coupling terms in your nonlinear terms in the Lagrangian? And then a comment, have you thought about looking on the other end if you have fixed point, far from equilibrium fixed points and spectral cascades? Can you learn something from those about the geometry?
So what was the question about the fixed point?
So if you go into the full nonlinear regime, you can reach new fixed points, far from equilibrium fixed points.
Oh, you mean in renormalization?
Yeah, spectral cascades from turbulence. Have you thought about this, and can you learn something about the geometry looking at those?
Okay, so let me address the third question. I don't know if you have time for the first one.
Try to make it brief, Achim, please.
All right. Okay, so here's the thing. The spectral geometry part of what I said is actually classical because you can do it for even a potato. You just listen to how the modes excite each other. You don't need any entanglement. You don't need anything quantum really in there. You can do it also for quantum, but it's really just spectral geometry in the sense of classically you can hear the shape of a vibrating potato if you make it vibrate strongly enough to get into the nonlinear regime, which also means you do not need to go beyond first order perturbation theory. Just the onset of these nonlinearities is sufficient. Just hearing how the frequencies excite other frequencies is sufficient. If you go to renormalization and you have non-trivial fixed points, it's overkill. It's all fine, you just don't need it in order to get the geometry from the correlators. But remember, what I said in the later part of the talk is going beyond that. I'm just saying, at that point, I was just saying, well, the correlators describe the matter, the correlators describe the geometry. So the correlators describe everything. And then from that perspective, at the very end, where I said, well, we have the partition function, and then its Fourier transform is the classical action, that's where renormalization and fixed points come in. But they do not concern the central part of my talk, which was to explain the generalization of Noether and how we can make spectral geometry work. I mean, what you asked is a good question. It just goes beyond what I said today.
Okay, so the last question, and I'm seeing people going away. Let's stay here. I'm going to make an announcement after this. So keeping you with those.
Free beer.
Very interesting talk, Achim. I've not understood whether your underlying metric information carried in it, it's just a background, or you can account for the evolution of the metric, or more generally, if you consider spinor fields of the tetrad fields and so on. How would you do that, this?
Well, it works for all wave operators. Regarding the other question, you asked whether sorry, what exactly were you asking again?
You are just recovering the metric as a background with no evolution, or you can allow also for the evolution of the metric, make a dynamical field?
Yes, the evolution of the metric, the whole thing. It's a space-time that we are recovering, not just space at a particular point in time. It's the entire space-time that you're recovering.
But you get Einstein's equations out of it?
Yes, that was in that paper with Barbara and with Marcus. We did that.
Okay. All right. Thank you very much, Achim. Let's thank the speaker again. Okay, so I know that you're looking forward to the break, but please remember that there's going to be the ISRQI general meeting And the RQI General Meeting would have a lot of surprises. So if you miss it, you may or may not regret it. Huh? Say again? It's going to be very special. Sorry, I didn't. Sorry, Fabio, it's my fault. I didn't understand. Please sit down and try to not to make much noise because we're going to begin the next session. All right, so our next speaker is Singh from IIT Delhi, and he's going to talk about checkpoints on the road to quantum gravity. So Suprit, floor is yours.
Thank you very much, and thanks to organizers for having me here. Thanks, Eduardo, for introducing me. I'm going to talk about checkpoints on the road to quantum gravity. It's a road where we don't really have much of a view. It's quite foggy. We're not quite there yet, and or the guidepost or any guiding insights are always helpful. So kind of like I put it as time before you had quantum electrodynamics. You had some semi-classical insights. So I'll be talking about those. There are also thermodynamic aspects of gravity, which in my opinion are a key to any theory of quantum gravity should in the low energy limit give those results. So they're like these guiding posts. And then I'll also talk about things related to entanglement in quantum gravity and semi-classical approximation. It's a bit of an obituary there, but I'll mention it. And then also how we things beyond that point. Okay, so let's begin. So as I said, there are examples abound where theories have guided observations, and then there are examples where experiments and observations have guided theories. So like the famous one is we had the tables of Uranus, and there were discrepancies which were found there, and Leverrier took the model that is Newtonian gravity and considered that there should be a planet, put the assumption that the Newtonian gravity is correct. So let's look at the perturbations by putting a planet there and find what is the location of that planet to give those discrepancies. And the astronomers looked at the place he pointed and they found Neptune. So the same Leverrier tried to also explain the perihelion shift of Mercury, but it could not do it because in this particular case that theory was not found to be correct because there was no planet found there. So there's here the observation guided a theory because Einstein kept computing various theories and he stopped when he got the right number. And of course when you have a theory you make predictions, and there were a prediction which was subsequently verified in the solar eclipse observations of 1919. Okay, so it's the kind of equipment which Eddington used at that time. So quite primitive, but still verified the theory for us. Here's another comic strip from Peanuts. They sort of say, they're talking about stars in the sky. So it says, if you know your stars well, you will never get lost in the woods. But she goes on to say that there's a star in the east. So if you follow that, you'll get to your camp. So he asks, what if it's not in the east, or probably it's the west? He says, is there an east star? She says, no, that would be too easy. It's actually a misconception. There is no east star or a west star because the earth rotates, but we do have a north star. So things are sort of the same in quantum gravity. So I'll put a quote here from Paddy's Thermodynamical Aspects of Gravity. It says, the fact that one can associate thermodynamic properties with horizons brings together principles of quantum theory, gravitation, and thermodynamics, and possibly offers a window to the nature of quantum geometry. So it's kind of like the guidepost there. So we'll dive in. So essentially we're looking at what we are is gravity-matter interaction. Okay, so there are prescriptions. How do you prescribe how to couple gravity and matter together? The predictions or effects. And there often are certain paradoxes which could resolve. So any theory of quantum gravity or description should resolve those problems. There's things like black hole information paradox. And then there are probes and experiments that we need to look for to sort of see whether we are in the right direction. And we have seen quite a bit of experiments during this, they have been put forward during this conference. So I'll mention a couple of prescriptions and also what are the effects that the current understanding has sort of given us from the semi-classical language. So in here, we're not quite quantizing gravity, but we're saying, okay, let's do it step by step. The first thing is you have classical gravity and quantum matter. The question is, how do we couple them together? It sort of brought me back to the first chapter of my PhD thesis, long back. It's more than 13 years now. So GR provides a self-consistent classical dynamics of the metric and matter. Geodesics on G, they give approximate dynamics of point particles. So there's no back reaction in this particular case. They are test particles, they do not curve the space-time. Quantum field theory on curved space-time, when we do that, is actually analogous to geodesics on curved space-time. We have matter states, we are working with fields. They do not back react onto the geometry, at least in one approximation. Then you go on to consider how do you actually take care of back reaction. But even so, this particular level, at this level, also we have seen a great deal of phenomena that has been unraveled. For example, we have seen the Unruh effect and the vacuum polarization in non-inertial frames. You have the temperature given by the acceleration of the observer, and there are various ways to look at it. You could look at it through the Bogoliubov transformation between the modes in two frames, inertial and non-inertial. You can probe via the Unruh Dewitt detectors, and but the thing to note is there is no outgoing flux in this particular case, okay, because it's time symmetric. So in fact, you can go slightly beyond this and consider thermodynamics of gravity in local frames. What do I mean by that? You go to a local inertial frame, and in that you consider a local Rindler observer. When you do that, this will be in any generic space-time, then you see that this temperature is still there, but then you also obtain corrections, which are, there are some other factors, and these other factors, this was something which was schematic illustrated in Paddy's reference, and then I went ahead and calculated this thing, put it up last year. So there are these factors which come up. Now these factors could be due to the local region which you are probing, and also curvature effects. I have not computed this, so there would be extra ones which would be curvature effects which would be there. So two kinds of effects come in. One depend on the size of the region L, and the other ones are curvature ones. So these thermodynamic aspects must be reproduced by any theory of quantum gravity in the low energy limit. So again, a checkpoint which is there. Then we have also had the Hawking phenomena, that is a pair production by black holes. And if you consider, for example, if it is in the simplest terms, if you consider any bipartite system of a classical C and a Q degree of freedom, a way to get semi-classical dynamics is usually what we do is we look at an effective action. We find that, okay, we cannot solve the full path integral. So let us integrate the faster degrees of freedom, which are quantum in this case, and then try to see what is the effective action. Imaginary part of that effective action gives us particle production. But this works if you can define in and out states. So this is a requirement which is there. So it requires existence of time-like killing vectors. If you do not have that, then the effective action, the out state is not there, it does not quite work. So particle production, as I said, is given by the imaginary part of the effective action, which is vacuum decay. It's actually difficult to incorporate as back reaction on the classical degree of freedom, because the moment you add in there, the effective equations of motion are complex, which we don't know how to solve. So this is a problem in itself. In fact, this was something which was also pointed out long back by Dewitt in his paper. So we also looked at another possible way to sort of can we look at the incorporate back reaction, although it was not completely, I mean, we could find particle production, but again, imaginary part, incorporating that is not quite an easy job. So this was, you basically look at path integral and try to see using the tunneling approximation, the tunneling interpretation, not the approximation. Wait a minute, something happened. Yeah, okay, it's back. Good. So it probably tunneled through something. So you see that the path, in the path integral, when you are computing that, the path becomes complex. So it enters a complex plane, and when the path becomes complex, it actually, you can also find the effective action from this and also get the information of particle production. So these are again an effect which is quantum field theory on curved space-time without back reaction. That's the complex path. So you could also look, as I said, there are other ways also to look at it. So you can also study Unruh-David detectors on the space-time. And then this brings in an additional thing that now there is an observer dependence. So you could have different kinds of Unruh-David detectors or different trajectories, whether they would be at fixed radius, circular trajectories, in falling trajectories, and you see a different phenomena emerging. You see that in these cases, we find they're just not one temperature, but they're two effective temperatures, and they're tied to the ingoing and the outgoing mode. Flux in this case, because you have a collapse, so when that is happening, you do not have time reversal. So the flux in this case is non-zero if you compute it in the Unruh vacuum. And again, it depends explicitly on observers and frames. So you could do this thing for different classes of collapsing scenarios, and things hold even in the Oppenheimer-Snyder collapse. And you can also probe the inside of the black hole horizon, with especially if you have in-falling observers. So things like something fishy happening at the horizon doesn't quite happen. The observers in-falling observers fall through as if there's nothing wrong at the horizon. Okay. So, but there is of course a problem, which I mentioned again, the certain paradoxes which arise, and they are arising because we are looking at half the game. We are looking at quantum field theory on curved spacetimes without any back reaction, and therefore there is a problem of information loss in black holes which comes around. I'll come back to it at the very end of the talk. So again, there are also applications which are abound in cosmology, and in particular in the very early universe and inflation. So I want to mention what are the problems here. There are some important questions, again, any quantum theory of gravity must address. There are questions of detecting the quantum origins, and tied to it, ironically, is also a question of how classicality emerges. But it's sort of mixed, because if you make everything classical, then you cannot detect the quantum origin. So it's a kind of you need some sort of a leeway there. The fundamental problem in inflationary dynamics is also that matter, the inflaton here, is broken down into two pieces. So you have a classical source piece which is sourcing the background, and the other are fluctuations that are quantized. So it's a very out of the ordinary supposition. You never break an electron into two pieces, that is something half of it would be classical and another one would be quantum. Matter is quantum through and through. So quantum field theory on curved spacetimes it has had its applications, but there are some issues with it for sure. Apart from doing field theory on curved spacetimes, there are also other effects like the Schwinger phenomena, and there are other questions as well in the domain. They're like resolution and censorship of singularities, the issue with the cosmological constant, not dark energy. When I say this, I differ it from the dark energy. Then also about compact dimensions, where can you find effects with which you could unravel or reveal the existence of compact dimensions. So I'll now switch gears to the next topic, which is going beyond quantum field theory on fixed background. That is, so as I said, quantum field theory on G is analogous to geodesics on G. Matter states do not back react onto geometry. But there are situations where back reaction can become important. And here is a particular one. So for example, modeling the mass loss in Hawking radiation when you are doing quantum field theory on Schwarzschild background. So it's a very simple calculation to see. For example, you have the Schwarzschild metric, there are two scales. So usually the way we incorporate back reaction is we would say, okay, the mass becomes time dependent, and also the Schwarzschild radius, because both are related. Now, black hole being a black body, you can find energy flux per unit time. This goes as T to the power 4, and you see the temperature drops as 1 by m. So you can find the rate of mass loss, and that turns out to be inverse of m. It's 1 by m square. So you see that it diverges in the limit of m going to 0. So it suggests there would be a huge back reaction from Hawking radiation. So it's an insufficient back reaction model. So we expect a series of approximations to sort of sequence of approximation to happen if you're going from a high energy to a low energy limit. So if you have quantum theory of gravity, then you would have quantum field theory on G. Something in between, there should be field theory on G with back reaction. Now we have a good understanding of only the last link in this chain. In this chain, as I mentioned, there are various effects that it has given us. There are ideas about quantum gravity, but there is no clear way to derive the middle link. So how classical gravity is coupled to quantum matter with back reaction. So one therefore provides some sort of a prescription again to handle this. And for gravity, it has been suggested since decades that we should consider the semi-classical Einstein equation. So this would be Einstein, the gravity, the geometry on the left hand side and matter on the right hand side, matter being quantum. These are operators, so therefore you replace these operators by their expectation values. Now there is there's no first hand way of deriving this thing by in principle, so it is something which is postulated. It comes with lots of problems. These have been noted down. To begin with, the right hand side needs metric. If you want to compute the expectation value, you need the metric, and you don't have it to begin with. The matter state, the evolution of the matter state is missing in this. You can posit that. Even if it is computed in a given state, so the expectation value of the stress energy tensor you could only compute for certain classes of special spacetimes. A generic way of computing this is also missing. So there are a lot of problems here, and I really wish that in some way an obituary for this approximation could be devised. And I'm going to mention one counter example where the approximation does not work. How can we do that? Well, to get a counter example, we really need to know a situation where we can study full quantum dynamics, where we can study something analogous to quantum field theory on curved spacetime without back reaction, and somewhere we could study the semi-classical approximation with back reaction, the way it was postulated in the previous slide. So how do we do it? We start with first find the counter example. We take the motivation from Newton-Schrodinger equations, but it's just a motivation. Once you have seen them, just throw them away. So you have classical and quantum degree of freedom. We posit a self-consistent model that is in the same way as postulated. You have the full Hamiltonian, and the Hamiltonian is replaced by effective Hamiltonian where the classical piece remains the same. The quantum piece is replaced by the expectation value. Now the thing which was missing was how the states evolve. Well, for that the evolution is given by the Schrodinger equation for the states, given by the quantum piece, and for the classical piece you take the Poisson bracket of C with H effective. So these two things together with the initial data can be solved self-consistently. So evolution of all observables can be obtained from these equations, and so you need some sort of a testing ground where, as I said, you can study a system fully quantum mechanically in the semi-classical approximation with back reaction, and then quantum system in a fixed classical background. That is, you don't consider the effect of the back reaction on the classical geometry. So we found such a system. But before that, to just mention, if you have a bipartite system, so you have a Hilbert space which can be broken down, any general state in this Hilbert space could be written as a simple product state, the superposition of the basis. So we look the measure which we are using is entanglement to study these systems, how to differentiate between them. So this gives you a bit, so if you have a bipartite system, you can bring in entanglement. So, and an example, simple one is of a Jaynes-Cumming model. If you have two systems here, there is an oscillator and there is a spin system. So this spin is coupled to the oscillator via this coupling term. So you can give an initial data and evolve it and study the evolution of the entanglement entropy, and that is something which we do. So you can have different spin systems. Here I have taken spin half and spin 1, and the evolution of the entanglement entropy can be computed by solving the equations given the initial data. So for our purposes to get a counter example, we select what we call as the double-edged oscillator. So what we have here is a harmonic oscillator which is coupled to two spins, not one. So we have two spins here and then the oscillator. So there are couplings G1 and G2, and in particular there can also be a coupling between them which is lambda. So if lambda is 0, then the two spins are coupled through the oscillator. So there are three well-defined models in this case. There is the quantum oscillator and quantum spins. This is the fully quantum picture. Then you have semi-classical oscillator with back reaction from quantum spins, and then you have spins which would just be evolving on a classical oscillator. The background is fixed. They are not back reacting, doing anything to the oscillator whatsoever. So here's the QQ model, the quantum one. So you have the Hilbert space. So earlier I had a bipartite one, now it's a tripartite. So there are three things: the oscillator, spin 1, spin 2. So you can write down the full Hamiltonian in this particular case. Again, the oscillator, the free part of the oscillator, the free part of the spins, the coupling between the oscillator and spin 1, coupling between the oscillator and the spin 2, and the coupling between them both, between the spins themselves. So it's a separable one. Keep in mind that in the Hamiltonian in this case is separable. Not always that you can have a separable Hamiltonian, especially in gravity. So since it is a full quantum thing, you know the Hamiltonian, the evolution equation is just the time dependent Schrodinger equation. The evolution is unitary, it's linear. Then you have, why is it not going ahead? Then you have the semi-classical model in which now we want to have back reaction introduced onto the classical oscillator. So you again have your oscillator, you have your spins. So the Hamiltonian is similar, except that now we say, okay, the spins evolve quantum mechanically, but for the oscillator we use the effective Hamiltonian by replacing the quantum operators with their expectation values in the state which is evolving given by the Schrodinger equation, and we obtain the oscillator dynamics from the Poisson brackets. Finally, what is analogous to quantum field theory on curved spacetimes is the model where you do not have any back reaction on the spins. The spins evolve in whatever the way they want to in quantum mechanically. There is nothing happening to the oscillator. The oscillator evolves with the Poisson bracket given by the Hamiltonian of itself. There is no back reaction in this particular case. But the oscillator does affect the spins. Okay? So this is the question is, what can just two simple qubits do to a harmonic oscillator? When can they really back react and make the oscillator go wild? Yes, they can. This is, for example, this is what happens when the back reaction is taken into account, the evolution of the oscillator in the phase space, and you see that this is the evolution which proceeds. So otherwise, what would have been a simple ellipse or a circle for an oscillator, it is a complicated evolution once the back reaction is incorporated. So therefore we study this system in three different regimes, that is characterized by the coupling between the spins, not the spins, so we take G1 and G2, that is the coupling of the oscillator with the spins to be the same given by G. So when the oscillator is coupled mildly to the spins, you do not see much happening to the oscillator. The oscillator remains the same, and you can compute the entanglement entropy of the spins, because those are the quantum degrees of freedom. You have 2 spins, so you can compute their entanglement and see how it proceeds. Finally, then you increase the coupling strength and try to see what happens. Once the coupling of the oscillator with the spins is increased, you see the back reaction coming in. So when you take a fully quantum picture, there is a oscillation, there is a back reaction. In the semi-classical picture, there is also back reaction, there is a change here. But when the oscillator is on a fixed background, the spins on a fixed background, they don't back react, it still remains the same. So there is an entanglement generation which happens, which is different from this particular case when the coupling is weak. However, note one thing, the order of the observables, it's 0.15 between 0.15 and minus 0.15, this is of the same order. Something is going wrong here with back reaction. So the semi-classical approximation with back reaction, like the way we put it in the semi-classical Einstein equations, is not quite working in this particular case. And the same thing is true if you further increase the coupling between them. You see that there is quite a bit of an agreement with of course, these two are different because there's no back reaction in this case. There is a full back reaction here, but it's a full quantum evolution here. But when you have a back reaction with the semi-classical thing, the order is way off. Okay, so these two are definitely different in both the cases. You have the entanglement generation happening much more so, and the dynamics is much more populated than this case. So to see the difference between the 3 schemes, we look at how the observables of the oscillator deviate, and we see that there is a deviation of from the semi-classical approximation. The classical background and the QQ are almost in agreement, but the dynamics with back reaction thrown in a la the Einstein equation, semi-classical Einstein equation, does not quite match. So there is therefore an issue here, and one possibility of a physical picture why this problem is arising. In the semi-classical dynamics, if you see that the state is going, so you have the Schrodinger equation, the dynamics is linear in this particular case, but in the effective Hamiltonian, it becomes non-linear in the state. Those non-linearities add up. So the semi-classical approximation therefore not works quite well. So the key points is low energy regimes look okay. But the prescription with the expectation value does not quite work. We do see entanglement generation when there is a self-interaction between them, that lambda is required to be non-zero. If you do not have a non-zero lambda, that is the coupling between the spins, there is no entanglement. Then there is a curious case for the semi-classical model where you have initial states for the spins. There is no entanglement induced for G is equal to 0, but lambda not equal to 0. That is, it is not coupled to the oscillator, but it's coupled between them, still there is no entanglement. Okay. So if you switch on the coupling with the oscillator background, entanglement gets generated. So this is, if the gravity comes in, you do get entanglement there. So there are questions, lessons for gravity. Sorry, Edward, how much time do you have?
You have 11 minutes.
11 minutes. Sure, thanks. So lessons for gravity. So it raises interesting questions for quantum gravity. If general relativity coupled to matter can be quantized, if you are looking at a fully quantum evolution, and evolution of initial state can be studied with respect to some time choice, how does the entanglement of matter and gravity evolve if everything is quantum? Do the initial product states become entangled? And at late times beyond quantum gravity era, is the entanglement driven to 0? That is, do you get back your quantum field theory on curved space-time without back reaction? That's the way you require it in various cases. So they are relevant, as I said, for the emergence of quantum field theory on curved space-times. So this is something, another work which we looked at. it's a hard problem, but you can look at it in cosmology. That is, you consider a Hilbert space of gravity and matter, and therefore in cosmology you can get a relatively easy Hamiltonian to play with. You have the gravity piece over here, and then you have matter piece over here. So matter and gravity are coupled via the scale factor. So this is an example of a Hamiltonian which I was referring to, which is not separable. You cannot separate into free part of gravity and free part of matter. I mean, the free part of gravity is there, but the matter always has this gravity piece there. So gravity cannot be turned off. So again, but if you have the Hamiltonian, the physical Hamiltonian, you can study the Schrodinger equation, time-dependent Schrodinger equation, and the dynamics. So it's as I said, it's not it's unlike the conventional bipartite system. So this is what we do. We performed such calculations for various classes of initial data. We had product states of matter and gravity. They are linear combinations, or what we call as multiverses. And then we have product states of another type which are not separable. And then we can also have initially entangled states. So here's an example which I am mentioning of what we call the multiverse state. So you have the linear combinations of this kind of state. So you have at A1 and A2. So that is what is happening here. So you see two states here. This is like a multiverse kind of thing, and then you can see what the evolution goes out. So is how they evolve in time with the Schrodinger equation. The evolution is completely unitary because this is fully quantum, and this is given by the norm staying almost conserved. And these are again the snapshots of how the wave functions evolve. So when you see you can study the entanglement between the two, and when we do that, we see that there's a trend which emerged that initially for the product state, for the entangled state, of course they will have some initial entanglement, but for the product state there is no entanglement initially. It develops, and subsequently for all of them there is a saturation of entanglement of entropy which comes in. This saturation sort of matches intuition because we would want to have a decoupling of the scalar and metric degrees of freedom. That is, the scalar field and matter and gravity should decouple as the universe expands. But there would be locking in some entanglement. An interesting observation to which I don't really have a proper answer to emerged. If you take a look at the saturation values of the entanglement entropy, and because the whole system is closed, so you can check what happens to the saturation values of the entanglement entropy versus total energy of the system, which is conserved. So when you look at that, you see this trend which emerges out. So if you look at for different data, so these are all different initial data. For each one of them, I find what is the saturated entanglement entropy, and I find what is the energy, total energy for that. There is a sort of a linear trend which is seen. Perhaps it is, it's like first law where there is a relation between entanglement, not entropy and total energy. There is no reason to expect this in a time step evolution with computation and diagonalization of density matrix at each instant of time. So as I said, I don't quite have an explanation of this yet. So there are two assumptions which went in here. The first one was the selection of a reduced phase space quantization. That is, we worked in cosmological space times. The full quantum gravity, nobody knows how to do it. And also there was a specific choice of clock. You select a time variable. Even within the reduced phase space, as I said, there are other clocks which are also possible. The only thing that we selected is called a dust time gauge. What it does is it yields a time independent Hamiltonian. What we saw there, the Hamiltonian was time independent. So it can be taken from beyond FRW to Bianchi cosmologies, and in spherical symmetry where you have a collapse happening, since this contains black hole solutions. When you have the full gravity and matter coupled with each other, particularly in spherical symmetry and a collapse scenario, with the Hamiltonian, perhaps you could resolve the information paradox. So there is a wide arena of testing semi-classical techniques, and that exists. Also in the experimental domains, the analog gravity models, entanglement witnesses, Schwinger mechanism, and quantum optics. I'll finally mention what I was going to about the information loss. This is just a recent submission which we made. We're looking at a gravitational collapse, and which is sourced by a classical field. So you have a classical field in spherical symmetry undergoing gravitational collapse. On top of it, we are studying a test quantum field, which is in a full numerical relativity simulation. And we find that this test quantum field, there's no back reaction as yet. We would like to incorporate that, but still, even without any back reaction, there are non-local correlations which emerge out. So initially, if you look at the phi-phi correlations, they're all diagonal, and subsequently with time off diagonal non-local correlations come out, possibly could resolve provide some hope to resolving the information loss due to these correlations. I'll stop here. Thanks.
All right. Time for questions.
Hey, first, thank you for the talk. I think I'm learning few new things, even if I talk to Vicar about most of this stuff. One thing which surprising, I'm used to the idea that entanglement, properly defined in mean field theories, is not changing. And you hear in two oscillators in a bit model have change of the entanglement or creation of entanglement of initially unentangled state. Okay, it follows from the mass. Can you give a quick explanation?
Because of the coupling between the two. The spins are coupled.
Oh.
Okay, so they're talking with each other.
Yeah.
So it's not through the oscillator. Yeah.
All right. So.
Thank you for the talk. So I have a question about the entanglement you showed concerning the first example of the fully quantum system.
Sorry,
the fully quantum system, so the
fully quantum system,
oscillator and the two spins. So you showed an entanglement measure
Yes.
between the two spins, right?
Between the
That's
spins,
one.
only between
But this
the
is
spins.
a tripartite system. So which measure of entanglement did you use?
The von Neumann.
Sorry?
The
von
von
Neumann
Neumann,
between
yeah.
the two spins.
Between the spins only. Yeah.
But you have an entanglement also between the spins.
Yes,
and the
it's symmetric. You can convert. So take it as a bipartite system, just the oscillator and two spins. So either
So you're measuring the entanglement between the oscillator and the
and
two
the spins
not
that can also
between
be-
the two
yeah,
spins.
yeah, yeah.
Okay, that
Yeah.
was the question. Okay, thank you.
All right.
Yeah, thanks. This is a very elementary question. What's in the cosmology part you did near the end, that you had multiverse and entangled and product, what's the distinction between the multiverse case and the entangled case? Is the multiverse like a mixed state or something?
It's a mix. So it's a superposition of two product states. So you would have you have gravity where you have the scale factor, which is there. So when you superpose it, you can have scale factor at one point, localized at one point, and also localized at the other point of two different. So that is like two different scale factors. Localized, yeah, the mix. Yes, yeah.
All right. Thank you very. Oh, there's one more.
Sorry.
Didn't see you. Sorry, Jerome.
Thank you very much. In this cosmological mini-superspace example towards the end, could you put up the Hamiltonian again?
Yes.
Thanks. So when I look at that, at first sight, it looks like there might be some sort of a singularity at A equals 0.
Yeah.
Could you comment on the character of that singularity and whether it needs some sort of a special treatment?
Yeah. So it so it's a quantization on a half line. So you need self-adjoint extensions.
Use this one and we take this.
Oh, okay. Yeah, so you need self-adjoint extensions. Yeah, yeah. So be taken care of. Yes. This was the self-adjoint thing on half-line. I think it was done by John and Gabor in one of their papers. Yes.
All right. Great. Thank you very much. Let's thank the speaker again.
One second. Just shortly, so is there anyone who gets reimbursement from cost and didn't sign this list today?
So it's 40 minutes. What I'll do is I'll give you a 10-minute warning,
Okay.
but that includes questions.
Okay.
So you want to finish earlier.
Okay.
You can think of it as 10 minutes as 5 minutes effectively.
And 5 minutes as a rule.
So this, I'll give you this.
Okay. Is there a pointer, or I did not bring one?
Pointer, yeah.
Okay.
Yeah. This will give you a pointer. Okay, so our next speaker is Miriam Weilenmann from the University of Geneva, and yeah, the floor is yours.
Thanks. Well, first, thank you very much for the organizers. It's been a very, very nice event, very many interesting talks, a beautiful location, so thank you, and also, of course, thank you for inviting me. So I'll be speaking about relativistically causal correlations, and for now I've put them in quotations because I know there are at least 2 different definitions one can have of them, but I will define what I mean. Also, I was asked to also speak about protocols, so wherever I can, I will also speak about how these things relate to cryptographic protocols. Okay, so to start, because we're quite a versatile group, I try to just give some also historical background of where this approach comes from. Okay, so kind of maybe the overarching thing of where I'm working is kind of we're trying to understand physical systems via understanding the correlations we can observe on them. So what does this mean? So one question we ask is, okay, what does physics imply for correlations? And I guess this we all know. There is, for instance, Bell's theorem, where we can see that different theories of physics lead to different correlations between measurement settings and outcomes. And in fact, we can distinguish between them experimentally. What is maybe less known outside of really the quantum information community is that we can also go the other way around. So we can ask, okay, if I have specific correlations, what does this imply for the systems? Okay, and in quantum information, this is something we do a lot. So this is the first chance for me to mention protocols. So there is a field of device independence where from correlations you draw conclusions about the system you're holding and then use this to prove security of some protocols. Okay, and these are quite old ideas actually that have been around for a long time, and I will say a bit more about this one. Sorry. All right. Yes, so what is the idea? Okay, so the idea between making protocols out of these ideas is, so imagine you want to do something in cryptography. So for instance, you want to do some protocol, you will need some randomness to do this. Okay, so you go to a company, you buy a random number generator. Now, okay, maybe you don't know the company so well, you don't really know, can I trust them or not? So what could you do? Okay, so maybe you can ask your friends whether you should trust the company, but maybe they also don't know. If you're experimentally well versed, you can actually open up your detector, you can see what is in there, and you can see, yes, I believe this is a random process or not. But if you're a theorist who is rather clumsy like me, there is not so much you can do. So all you have is your generator and the numbers come out. And from this, you cannot really tell whether you can trust this, because what could the company have done? So they could have just one random number generator in their office. They could produce a random string that is really truly random and just put it in all the generators they sell. Okay? So in a way, you have random numbers, but the company knows them. And in fact, they can also sell those numbers to anyone they want. And so these numbers are not really private. Okay? And so just from having this thing and looking at what comes out, you cannot really tell anything. Okay? And then comes in the idea of device independence, which is really trying to remove this trust into the manufacturers of your devices. Okay, and for this we can use physical assumptions about physical systems. So, in fact, what we can do is that if we have certain correlations between parties, so now I assume the manufacturer, rather than giving me a detector, he sells me a whole setup. So he sells me some source and two devices that I share with my friend, and now we observe correlations. And now the point is that if we believe that quantum theory correctly describes this experiment, just from the correlations we can draw conclusions about what system is in there. Okay, so for instance, if we do a Bell test and get 2 root 2, we know essentially there is a maximally entangled state in there, and we also know it's the usual measurements, all up to local isometries, but somehow there is strong entanglement in there. At the same time, this then means if me and my friend were maximally entangled, a third party cannot at the same time also be maximally entangled with what we have. And so in a way we can reduce the knowledge any party can have about our correlations. Okay, so this is kind of the basic idea. So rather than trusting the manufacturer, we do statistics, we conclude something about the physical systems in the device, and in fact, based on these ideas, one can then, for instance, do randomness expansion or quantum key distributions where the rates are given asymptotically in terms of these quantities. So this is just the basic idea. Why this works, proving things is very different, but this is kind of the intuition. And so in that sense, really looking at correlations can be very useful also for protocols. Now, as I said before, I mean, this works if we believe that the setup we have is correctly described by quantum theory, and also that any adversary is restricted to only know quantum theory. So if they have a better theory that maybe can describe this better, of course they can break this. And I think this is what relates also to this community. So what if we improve the theory we have? Can we still do reasoning like that, or do all the things people are currently doing with device-independent cryptography? Does everything break down? Okay, so this was the detour to the protocols. Now, then, okay, so maybe we don't want to restrict to quantum theory. Could we just ask, well, does relativity, and in this case it will always be special relativity, impose any restrictions also on my setup? So, and actually this question was kind of, I think, first asked in this paper, where they asked, well, actually if you look at the Bell test, like CHSH, quantum theory does not get the full algebraic value. So you get the 2 root 2, but the algebraic maximum would be 4. Okay? And then the question is, well, is this somehow due to special relativity? And the reason is no, because if you just impose constraints from relativity, you could get 4. And in fact, the constraints that are imposed, if you now assume Alice and Bob are just space-like separated somehow, when they do that are just these. So you don't want that Alice's input can affect Bob's output, because she could use this to send him a signal, which you don't want in this case. Okay, and so this imposes a strictly larger set. Now you can ask, well, what does this imply now for my cryptographic protocols? And this has been looked at a while ago, and I think the results are not very, very promising. So there are problems with trying to restrict the adversary just to use non-signaling. As far as I'm aware, there is no like clear no-go theorem though, so it could be that one could still do something. Okay, what I also want to stress, so in this case actually, you can also build theories that reach all those non-signaling correlations. So we also have ways from the inside to build a theory that does this. They might be a bit dull, but you can do this in this case. This will be important later. Okay. So then the question is, okay, what happens if we go to a multipartite scenario? So we have more than 2 parties. And now it's not so clear how to generalize these constraints. So, and there are 2 main, I would say, kind of avenues. The first one I will call standard non-signaling, which just means the input of no one should be able to affect the correlations of any of the other parties if they're space-like separated. And it's given like that. Yes, here the input of Z should not affect the correlations of AB and so on. And this also implies analogous constraints for the single parties. Now, already in the 80s, 90s, there have been suggestions that maybe this is not a thing to consider, but maybe weaker constraints suffice. And the idea behind those works, well, I'll paraphrase as follows. So assume you have 3 parties now. They're not arranged like this, but they're arranged on a line. So it's Alice, Bob, and then Charlie. Now, maybe it's not a problem if the choice that Bob makes can affect the correlations of Alice and Charlie. So in fact, this one you might not need, because you cannot see this locally. So Alice cannot see whether Bob affects the correlations with Charlie, and Charlie cannot see this individually either. To actually see this, they need to come together. And they can only come together in this setup in the future of the other party. And so maybe this does not lead to any consistency problems, so doesn't introduce any loops or anything like that. Okay, and so these were the proposals. And okay, I will illustrate this also with the original example they gave in this second paper here. So we are in this setting I said. Okay, you can imagine that Alice and Charlie here, they are doing a usual Bell test. So in fact, if I just write the probability distribution in a table, so okay, here each box is corresponds to a setting for Alice and Bob, so X0 and Z0, X0 and Z1 and so on. And then the outcomes are the 4 outcomes are here. This would be what you get if you get the maximal score, the maximal quantum score in a Bell test. Okay, this is what it looks like. Now, okay, Bob sits between them and he does nothing, so they do the Bell test. Now in this paper, okay, the intuition is, okay, now Bob has some mechanism that he can turn on. And after he does that, instead of doing a Bell test, in fact, what they get is just, they are always perfectly correlated. Now, locally, they cannot tell, because you can see if you sum here these two, you get a marginal of 1/2 here as well. So you cannot really tell whether you're in one or the other situation if you're one of the parties. However, if you come together, I mean, the functionality of inputs and outcomes has been changed from this to this by Bob's action. So if you come together, of course, you can tell. And their rationale is, okay, this might not be a problem. Okay, and in fact, this reasoning is not really quantum. You can, in principle, do this classically. So you can have the parties do something where they're always anti-correlated. You can have then Bob just change them from anti-correlated to correlated in some way. And okay, I think this is the simplest thing you can do. And okay, I will call this jamming according to this jamming intuition that this was introduced with. Okay, so this was the idea. And now, more recently, this has been generalized to beyond this 3-party situation that we have seen. Okay, now you can have as many parties as you want, arranged in however you want, and essentially the conditions you should impose are those. So essentially what it says is that, okay, if you have a set of variables, then there should only be, the correlations of those should only depend on choices made in their joint past. Okay, so something that where if the intersection of the future of these exists outside the future of a variable, this should not be able to affect it. But if it's fully in the future, then we don't want to necessarily impose that, which is kind of the intuition I gave in the 3-party example before. Okay, so it's just a generalization. Now what we can say that in principle defining these sets of correlations is independent of changing reference frame, because these inclusions of Lycons don't change, but there is actually no underlying explanation of a theory or something how this could come up. So there all the explanation people have come up with would very much depend on that. At the same time, okay, there have been papers hinting that this could be something that could be relevant for future theories. At the same time, though, it's definitely outside of all the ways people are currently building theories. So for instance, we have had Paolo's talk, and the GPT framework is very close to the OPT framework he presented. And in this, for instance, the standard non-signaling conditions are naturally built in. So there is no hope to actually have an example. And I think in this it differs very much from the standard non-signaling, because there we can build theories and actually see what would happen. Here it's really just an outside description of some set where we have currently no idea what it means. Another thing I want to point out, so there is also causal modeling for these correlations, and this is something Vilasini works on. Okay, so this is essentially what is there, and there is now some strong no-go theorems for cryptography in this case. So what is there? So first of all, we had this intuition in the quantum case that if two parties are maximally entangled, the third party cannot. And the same goes for non-local correlations. If they have strong non-local correlations, the third party cannot. This breaks down in this set of correlations. So if you take standard non-signaling, it still goes through, because 4 here is the algebraic maximum of the CHSH value. If you take these relativistically causal correlations, there is no such thing anymore. At the same time, so this was in this first paper, and then there is a follow-up with actually a no-go theorem that says that in cryptographic protocols, the way we build them currently in the quantum case, such protocols, you will not get positive key rates anymore. Okay, so they are quite restrictive statements. Okay, now this is somewhat interesting, but okay, what for me is a bit unsatisfying is it's really a set of correlations where compared to the other sets, we don't know what the theory would look like. And so what I was interested in is, okay, if I really start from the premise, I have this set of correlations, what will this imply for the world we live in or the systems I can have? Okay, and here I come to kind of my little contribution, which is about monogamy relations that come up if you take this set of correlations. Okay, so to see this, the simplest example needs a bit more than just 3 parties now, so we have 6 parties. And I assume I can write them as arranged in this way in a 2D surface. And you can see that we have this structure that we've seen before, essentially along each of the sides of the triangle that they're arranged in. Okay, now what I can prove then is that so first of all, I actually don't need all of the variables, so I just look at for some variables I look at the outcomes, or not all for some parties I look at the outcomes, and for some I look at the inputs. Okay, now if I do that, and I take all the variables to be binary, what I can actually prove is that I have such a relation. Okay, so what does this mean? So this is the mutual information that nicely characterizes how much information the variable, in this case u, has about the other two. Okay, so if we have 0 mutual information, the two factorize, so there is no information. And otherwise, well, there is, and then, okay, in this case it's 1 if u has full information, because we have bits. Okay, so this really captures kind of a monogamy relation, because if I use this jamming functionality from before, one of them will be 1, which means that the others have to be independent. Okay, so somehow one variable here that is really separated from the others can affect what the others can do, whether they can use this mechanism or not. Okay, and this is a relatively strong type of monogamy relations that comes out of this. Now, it's not only for bits, you can also do it in a cardinality independent way, and you get this relation and many others. This is just the one that looked most appealing, so I put 1 here. Right. You can also compare this to the standard non-signaling that we've seen before. So you can see here, you can, for instance, find an implication of CHSH for entropies. And we know that this, so here in the classical case, this will just be positive. We can see that in the non-signaling case, this is kind of this trade-off we have seen before in a different way, still holds. In this relativistically causal case, there is still something non-trivial, but it's much weaker, so we don't have this relation anymore. This just to compare to previous work and also to see that, I mean, it's not a set where you can do everything. There is still restrictions, but much less. Okay, how much time do I have actually? So half. Okay. So maybe I can tell you a little bit about how these come. So how do we get such relations? So there are these approaches, starting from this paper here in 2012, that derive constraints for actually classical networks. And then there are quantum extensions, non-signaling extensions, and now relativistic causality extensions. And the basic idea is that entropy is a nice way to encode conditional independence. So if you have that two variables are independent condition on another, you get such a linear relation on entropies, which you can easily work with. And so what you can do, if you have such a setup, you can just impose all the constraints on entropies that you have. You will have maybe unknown variables in your network. So in the classical case, you could have latent variables, which you want to trace out afterwards. So what you will do is just take all the variables you have. So this is an example with here maybe a classical variable that I want to trace out, and here a jamming variable, which I introduce with these arrows. I put all the possible properties I know for entropy, so which is a set of inequalities, some independencies. So here, this type of independence, okay, I don't think I will speak about this. There's just some type coming from the classical case, and then there are these independencies that come from the non-signaling constraints or from the jamming constraints. I put those all in, and I project the scenarios to the entropies I care about, and I will get kind of a set, a convex cone of things, and this will give me these types of monogamy relations. Okay, so this is the basic principle. So it's relatively simple to describe these things in entropies, whereas if you do probabilities, you'll have a polynomial approach, and it's much harder to deal with. You lose some information though, but okay. So this is just very briefly, and for the experts, yeah, this is where we change the approach to do the relativistically causal. So we add nodes, but then add independencies as well, and so yeah, that's how it goes. Okay, right. But now, okay, we have these relations, but so far this is still just a relation on entropies, and it doesn't really tell me anything yet about the underlying theory. So I'm wondering, can I say anything about what theory I can build now, because this was the original motivation. And the answer is, well, it doesn't give me a theory, but at least it gives me something. So what I can see from this is that what I cannot have in that theory is that there are really parties, like the original intuition in the works I presented, that have a mechanism that can do this jamming, okay? So there cannot be agents that actually exploit this. And at the same time, stay in this set of correlations. Okay, and the argument is relatively simple. So assume you had such a mechanism. So, okay, I've removed one of the parties now. I just have this angle now. So assume, okay, the parties decide either to do nothing or to change the correlations to that. Now I can see that if actually the probability that they change the correlations is bigger than 1/2, this relation that the correlations should satisfy is violated. Okay, so I get the contradiction. So I cannot at the same time have relativistically causal relations and this mechanism. More in a different way, if both parties would have this mechanism, what they can do is turn it on at the same time, which means that the variables satisfy this relation. What this then means is that actually the party controlling U can signal to B, C, and V, which can meet somewhere here, which is not in its future. So you can really actively use this mechanism to signal. Okay? So what at least this tells me is that I cannot really, I mean, what this relativistically causal set does is not really generalize this idea of having jamming, but it's characterizing something else. So there must be some kind of global mechanism, something a bit conspiratorial, that decides how variables can influence others. And so I think in that sense, it needs a new way of thinking about how we build theories, because usually we start with small things. Well, at least in the quantum info community, you start with small things and build things up, and okay, this doesn't really work in this case. Right, now what about cryptographic protocols? So I think there is an effect, but the many question marks show I don't really know. So what I know is that some of the arguments that have been made against against protocols to still work in this relativistically causal way won't hold anymore. So for instance, this argument that when two things are strongly non-locally correlated, a third one cannot, that this breaks down, I think one can leverage this by using monogamy relations. Because what you can do is you could introduce some other systems, and if you actually observe that that system affects the correlations, kind of it blocks others from doing this. And so I think there is a clear intuition that some of the arguments made there, they don't go through in this simple way. What is less clear is this no-go theorem that I've seen there. I don't know if there's any way to come around, but I think, okay, maybe more research and more is needed there. But I think what this shows a bit is that, okay, if we really subscribe to these correlations, I think it's not enough to just argue from the correlations and where the variables could be that affect each other. But, okay, we'll actually, like in the standard non-signaling case, need to first build an underlying theory and then argue from that standpoint to really say something in these cases. So it's a bit of a two-week thing. Okay, right. So what I wanted to tell you is, okay, a bit where this approach comes from, where its successes are in the quantum case, and also where now the limitations come in if we try to go beyond. At the formal level, there are these monogamy relations that I think are important to specify in addition to just a set of correlations, because it's kind of a new feature that is less innocent than the set of correlations makes it look. I think the advantage of the present approach is that, okay, we're really just starting with this premise of having these correlations and then seeing what we get from that. And often, okay, at the debate of whether these correlations make sense or not, start by adding additional features and then asking in that sense, and then, okay, it's a question of, are these additional assumptions reasonable? In this case, there aren't really any. Right. Now, what I think also we can learn from this is that there is this really global nature of these monogamy relations, and somehow this, I think, also has effects on the causal modeling that has been done in this case, because somehow, yeah, it's a bit strange to have this global effect, but then describe the whole thing in a causal model, and I think there are new questions that will need to be answered, and whether, yeah, the causal thinking is really suitable even for this type of correlations. I would be interested what other people think about it. And especially also concerning cryptographic applications, which I mentioned already, we're very much used to thinking about an agent doing these things from this set of correlations and the relations they satisfy. It's not at all clear whether this is the right way of thinking about this. So I think there are really, really new ideas needed. The last question, which I think is very individual, are these correlations really plausible for a future theory? I'm a bit skeptical, I have to admit. I would be interested to hear other opinions as well. For me, this general kind of global relations between space-like separated things is somewhat unsatisfying. At the same time, I think it puts problems on doing also experiments in physics, because usually we assume, at least in quantum, that, okay, we interact with some environment and you have some kind of condition that local things affect you. If it can be something at the other side of the universe that just changes your correlations, this, I think, puts real problems. But okay, maybe one should stay more open-minded, and okay, I would be interested if someone has a different view. For me, this is rather a negative result, but yeah, we'll see. Okay, and I think this is all I wanted to tell you. Thank you for the attention.
Okay, we have time for questions. I see 1, 2 for now. If you want to ask questions, keep your hand up when I see it. So.
Thanks a lot for the nice talk, Miriam. I want to understand a bit better the first point of your summary. Like, so you explained nicely that the monogamy relations suggest some features you have to give up for these relativistic causal correlations. What exactly would those features be? Is it, if I understood your construction correctly, you suggested that in this extended configuration with sort of 3 parties who could jam each other's correlations, you could have some violation of like signaling or relative, like no superluminal signaling. So is that somehow suggesting that maybe these correlations are not so relativistically causal after all? Or what would be your take on that? Like, is it violating some relativistic causality principle or some other principle?
Okay, I'm not sure I completely understand. Right. Okay, so I mean, but this can be because I'm not open-minded enough, no? So for me, it's kind of, okay, there are these 3 variables, and clearly what they can do affect, what they can do is affected by what someone else somewhere else does. And for me, thinking in a causal modeling kind of type, as you said, this would somehow require a common cause. Mm-hmm. So somehow what is unsatisfying is that you have these independent things, and they have effects, but how they can have effects is in a way restricted by things that is not a common cause for them. So somehow there must be a link in this case. I think this is where, for the causal modeling, the question is, because I think this has not been considered so far. And I'm wondering then, so because I don't see a way out, for me it's a question, does thinking in terms of causal modeling really make sense if you'd have a theory that satisfies this? But okay, I don't have an answer. I mean, this is something to
Okay,
to
yeah,
think
we should
about.
discuss this a bit more. I would be very interested to. Yeah, thank you.
Thank you for the nice talk. I was just curious, have you considered what the perspective is for EPR steering? Because I'm trying to figure out what kind of influences on systems you're worried about being uncausal. Because I mean, you could certainly EPR steer without violating sending actual information faster than light. Is this compatible with your view, or?
Yes. So steering, no, you describe in the quantum case. And quantum theory, I mean, it satisfies non-signaling in the stronger sense. So it satisfies this type of non-signaling. So now the question I'm asking is, okay, it has been suggested to relax this. So you would have to describe your steering experiment in a different way. So there could be someone sitting in your steering scenario and somehow affect both sides in a way that, okay, in the steering it's a bit difficult because you also have the communication link. So one will need to think carefully of how you could put the parties, but maybe you could put 2 parties in between and one that affects those and then have kind of like a relay. So it would be something that goes beyond how we describe steering now. So I think quantum theory and all the theories people have built in at least these kind of GPT, OPT communities kind of go into this. And now there is this more out there proposal that we don't really understand so well. And okay, I was trying to see how this works. So from the monogamy point of view, you also have monogamy of entanglement, but there it's like you have an entangled state and kind of it breaks down. Here you really have kind of just setting variables of space-like separated agents where, okay, we always assume that there is something like free choice here, that they chose freely, but at the same time they cannot choose what they do freely. So in a way, it's stronger in that sense, the monogamy. So it goes beyond a bit. I hope this answers your question.
All right, any other questions? Final one more if you Do you have any? Well, if not, let's thank the speaker again. Thank you very much. Before you go away, there's several, I see Gaetano probably has an announcement, but I have an announcement too. We know the room for the RQI meeting is going to be room A4. That is the air-conditioned parallel session room. Okay? So that's where it's going to be. And it's going to start at 5, I believe.
Yeah,
something
or 5.
So 5 p.m. when you go for the break. What's that? 4:40. Okay, 4:40 sharp. Okay, so don't extend your coffee breaks. A4. That is the parallel session talks room, the one that has air conditioning. There are 2 of them. One is nicer than the other. The nice one.